clipboard. Got it. Okay, that has demonstrated the utility of key point-based grounding for manipulation as well. And key points here provide also this flexible representation space to handle both scene and object semantics, unlike more granular visual representation like bounding boxes or segmentation masks and so on. So Clipboard, though, did a lot of planar pick-and-place scenarios, limiting its applicability to really 6-degree of freedom domains. And so follow-up work like this one, for example, RobotMu, also demonstrates the value of grounding via pre-trained internet-scale vision language models. And these works still consider pick-and-place applications at the scene semantic level and not so much at this object semantic level that we are interested in, since current VLMs struggle with object semantic understanding. So to extend to more complex manipulation tasks, we have these works that actually rely on large-scale data collection efforts in the order of many months to train new 6-degree of freedom skills that are reliable and precise enough for deployment. And so then in contrast, PERACT is work from CoRL about a year ago that proposes a sample efficient approach to instruction following. And PERACT trains a transformer which takes language inputs and a 3D voxelized grid of the scene and outputs discretized actions in the form of waypoints. And this end-to-end approach can leverage as few as tens or hundreds of demonstrations, but ultimately struggles with high precision tasks due to this inherent discretization of the visual scene from visualization. So we recognize in this particular work that I'm presenting today that current instruction following frameworks lack an object-centric representation to link instructions to actions. And we posit that key points offer a way to ground both scene semantics and object semantics, but also provide a way to condition downstream 6-degree of freedom manipulation for precision execution. And so, so here's just an example, again, of what we're going for here. Our proposed approach is called KITE, Key Points plus Instructions to Executions. And KITE begins by taking a language command and image as input, and then queries in LMM to determine an appropriate skill from a library of skills. And meanwhile, the language input and image serve as input to a grounding module, which outputs a single-step look-ahead key point identifying what to manipulate. And critically, this key point does not contain sufficient geometric information to plan 6-degree of freedom actions. Therefore, what we do is we deproject the associated depth image to a 3D point cloud, aggregated across multiple views, and then we annotate this point cloud with the deprojected key point as a means of conditioning the manipulation policy on the key point. And so finally, the annotated point cloud and skill semantic label serve as input to the acting model, which infers the parameters of the chosen skill and then executes the skill policy. So in summary, KITE begins by grounding a language command in the visual scene, inferring the appropriate skill, and executing a parameterized key point condition skill before replanning from new visual observations and instructions. And so in this manner, KITE is also able to do long horizon manipulation while retaining precision and 6-degree of freedom reasoning at the individual skill level. And so just a few notes on the training. So we actually collect a data set of kinesthetic demonstrations to train both the grounding module and the acting module. And the training of the grounding module basically, again, takes the instructions and the images input, and then basically trains this key point inference model. We also use this kinesthetic demonstration to train these skill policies that are basically waypoint policies that take actually the annotated point cloud as input. Okay, so experimentally, we validate KITE against methods that either do not leverage key point-based grounding, like PERACT, for example, or do not leverage a library of skills, like RobotMu. And PERACT is an end-to-end voxels to actions approach, omitting skills altogether. And RobotMu is similar in spirit to KITE, but replaces the learned key point model with a VLM. And so this is intended to ablate for the effectiveness of our learned key point model at identifying both scene and object semantic features over a pre-trained VLM. And so we evaluate each method on a suite of 3 real-world experiments: long horizon tabletop manipulation, semantic grasping, and coffee making. And semantic grasping is meant to stress test Kite's ability to handle object semantics not addressed in prior work. And we evaluate both scene and object semantic awareness in the other environments. So, okay, let's look at the long horizon task. And so for this environment, we evaluate all methods across 3 tiers of difficulty, varying semantic and visual complexity. So tier 1 includes fairly simple decluttered visual scenes and straightforward instructions like open the top drawer, pick up the lemon, and so on. And tier 2 and 3 consider more cluttered scenes with visual distractors like clothes and larger quantity of diverse objects. And and some examples of more free-form language include those that you see here, like give the top drawer a tug and so on. So after training the open, close, pick, and place skills from 50 kinesthetic demonstrations for each skill, we aggregate these demonstrations into one data set with which to train per act, one of the baselines, and we train per act in an end-to-end fashion and evaluate its tier 1 performance. And so here you see some of these examples that we found, and we observed that PERC demonstrates some performant instruction following with individual skills like pick and place, as shown in this first successful trial. However, due to the inherent discretization of the scene, there are some struggles here with precise manipulation. And there are some more details on this. So overall, PERC performs the best for cabinet closing and grasping, but compounding errors render this approach kind of infeasible for long horizon manipulation and more complex tiers. And next, we evaluated robot Moo across all tiers to implement this. We prompt an LMM with a given language prompt to identify objects of interest, and then use open vocabulary object detection via grounded Dino and segment anything to generate key point candidates. And so here is an example for this. We see that the proposed key points struggle with object semantics, like identifying the right cabinet drawer for given instruction. And in this case, no top drawer was identified actually at all. And this turns out to be a frequent failure mode for this case. So there's some struggle with multimodality here at this object level. But if it does actually identify, for example, heated handles, it's actually really precise and can make use of these skill-conditioned Kite manipulation, or these skills that Kite uses, and it's conditioned on key points to make task progress. Okay, so especially for pick and place, this works really well, and it's definitely a substantial gain in performance. And finally, we look at Kite, how Kite does. So here you see that in tier 1, Kite is able to effectively leverage its learned grounding module to identify object semantic features like handles, or scene semantic features like the lemon object instance. And in tier 2, Kite performs similarly, but we observe a slight performance decrease as the degree of clutter increases. And for tier 3, we consider more free-form language while matching the visual complexity of tier 2. And Kite can still perform semantic grounding and manipulation subject to distractors like the sweater and more ambiguous instructions. So this is kind of how this looks like overall, where we outperform these 2 baselines that we re-implemented. And this suggests really the benefits of both key point-based grounding and a learned library of skills. Okay, so next we wanted to look at these very specific object semantics in the experimental settings of semantic grasping. And so this really entails grasping of specific object parts like the cap of this marker, the label or middle of a marker. And again, for these experiments, we trained the key point grounding model from a data set of 300 images annotated with a paired key point and language instruction. And we test on both seen and unseen object instances across the categories of rigid objects, deformable objects, and articulated tools. And so here we show a bunch of samples of the diverse object and language pairings considered. So for this T tool, for example, it's like the left and the right handle. and so on. Yeah. And for the deformable object category, we consider a range of stuffed animals and instruct Kite to grasp by different body parts, head, nose, arm, belly, tail, and trunk or foot of these deformable objects we're considering. So this is also working fairly well. And we also looked at this particular task of coffee making, where we train again, 3 skills from 50 demonstration each. Here, for example, you see this reorientation and filling the mug with the red pitcher and so on. Okay. Okay, so while Kite demonstrates some promising results for precise 6 degree of freedom semantic manipulation, we also acknowledge there are definitely some failure cases. First of all, each skill is trained from around 50 demonstrations, and we know that skill imprecision can occur, especially for fine-grained tasks like pouring. We can also see this failure mode occur with grasping, which will require very closely aligned end effector and object geometry. And for placing, any slight imprecision in the height at which the object is placed can lead to a failure of the sort where the action is executed open loop and disturbs the environment. Finally, Kite is key point condition. So any inaccuracies in grounding can lead to incorrect manipulation. So sometimes the predicted key points are wrong, but not unreasonable. It's often like a semantic confusion, so like the wrong handle on the cabinet or things like that. So just to summarize this particular work, we presented a framework called Kite, and it addresses this problem of semantic manipulation consisting of both the scene level awareness and object level awareness. And it achieves precise 6 degree of freedom instruction following by leveraging these key point-based grounding and a learned library of key point condition skills. So with this, I want to go over to the next work that I want to talk about. How much more time do I have? Sorry, I kind of lost track of when I started. 10 minutes? Perfect. Okay. So we are in the language and robot workshop. So I just showed you a work that actually can ground fairly precisely instructions in the image using key points. But we also noted that actually language can be quite tedious, especially when it comes to very complex scenes. So another way on how to communicate manipulation goals to robot is actually by using sketches. And so this is this work that I going to present to you as well. So we consider the setting of goal-conditioned imitation learning. And we note that language, as I just showed you with this work on Kite, can be really convenient for users to provide, but it can also be limited in how expressive it is, dependent on the scene complexity. And another very common way to provide goals to a manipulation robot is through goal images. Through goal images, but it's not always available, or it can be actually very overspecified. So here's some examples for where language might not be super convenient, right? Imagine you want to set this beautiful table and someone tells someone to help you with it. When you use language to describe this, it can be actually either fairly ambiguous, like this example, put the utensils next to the plate, or it can be super lengthy, right? Especially for a complex scene like that. And if you want to correct someone, again, it might be fairly tedious to do that if you only have language available. So the other way you could think of is you could just provide this image here that I'm showing you of this beautiful table as a goal image to a policy. But that actually is kind of inconvenient because it means you have to set maybe the table exactly beforehand, or it's fairly environment specific, right? You know, what if you want to reuse the setup next year with a different tablecloth or different kind of plates and so on. So what we found is actually would be an interesting idea for a robot to be able to do is to act upon sketches that a user provides. And so why sketches? Well, there are actually, here are some examples of where this might be useful. You're already seeing the table setting, but you could also imagine you're moving house and you want to provide the movers with like a quick sketch of where everything goes. So wouldn't it be great if your robots could parse the same sketches? Or think about assemblies, like here you have the example of an origami, or you could think of IKEA furniture or something, right, where you always have these step-by-step instructions that typically come in these abstract drawings. So a sketch in these kind of scenarios could provide easy sub-goals. And really for these more complex setups, anything would take more time than actually drawing a sketch. Maybe some variation depending on your ability to sketch. Okay, so that was some background motivating the use of sketches. And so let's look at how we formulated this problem. So basically, we formulated as the problem of learning a goal condition policy, where we basically have this policy, a pie sketch here that takes a goal sketch as input and a history of observations and has to map it to some actions of the robot, right? So that's that's the policy that we want to learn. And so basically what we did here is to use to build on top of prior work like this RT1 work that basically takes as input a sequence of images and again only a language instruction, puts it through a transformer-based architecture and outputs a bunch of actions for in this case, this mobile robot. And instead of conditioning on language, as in this vanilla RT1 work, we were interested in actually a condition on a sketch by concatenating it with the history of RGB images and using a goal sketch as input. Okay, so basically we adopt pretty much the RT1 architecture here. And then what's the challenge? The challenge is actually get these sketches at scale to then train this policy, right? So we have this original RT1 data set that consists of 80,000 trajectories. Now the question is, how do we get 80,000 sketches to pair them with these 80,000 trajectories, right? We really don't want to draw them by ourselves. And so what we propose to do here is to use a learned image to sketch translation network, where we take a pix-to-pix GAN model that translates RGB images to paired sketches. And so how does that exactly look like? So here we have these goal images that we get for each of the 80,000 trajectories in our data set, then use this pix-to-pix GAN to convert them into sketches. And these would hopefully be our goal images that the robot can execute on. So how do we get this pix-to-pix GAN? We basically pre-train this architecture on a contour drawing data set that has 1,000 images paired with crowdsourced sketches like the ones you see here. So these are sketches for these particular images, each produced by a different user. And you see they vary quite a bit in level of detail, for example. And then also Priya, in this case, who is sitting here in the crowd, like over there, wave Priya so that everyone knows you. You can ask her later about the details of this work. She actually drew herself, like in this way, 500 different drawings for this particular RT1 scenario. And these 500 drawings, including these augmentations that we did here using color and define augmentations like translation and rotation in the plane, were then used to fine-tune this particular network. Okay, and so these are then the generated sketches that are the output. We also augmented, as I said, with affine transformations, but also with colorization, this training data set. So here's the full data set generation pipeline where we take the 80,000 trajectories that we have for training. We hindsight relabel the last observation of the goal image, use our pix-to-pix GAN to generate a sketch, and then use that finally as the last image. Okay, so now we have our data set, and now we can use it to actually train this RT sketch model. that takes as input to images, history, basically observation, and a goal sketch. It's concatenated with a goal sketch, pushes it through this transformer-based architecture, and outputs basically appropriate actions. And there's some detail on the training, where during training, we also further augment the training data set with very cheap operations, like using the Sobel Sobel operator to get more detailed edges, or colorizing the sketch. And then during training, we basically select one of these augmentations. Yeah, and here's some of the interesting experiments that I just want to show. So we wanted to test a few hypotheses. Of course, first of all, we wanted to know, can this architecture at all work on sketches? Then we wanted to know if it is robust to different levels of details, whether it can also work when there are visual distractors in the image, or what happens if language is actually ambiguous, right? Like, do sketches actually provide more information? So how did we study this? We used different metrics. The first one is human assessment, where we actually ask people to provide a Likert rating on this score from 1 to 7 in terms of semantic, what they thought, how good the robot built the semantic and spatial alignment of this particular task. So here you basically see the example questions that the people had to answer. And then we also looked at pixel-wise error in achieve versus ground truth goals via manually annotated object centroids. Okay, so the first hypothesis is, well, does RT-Sketch work? And especially we wanted to know this in comparison to vanilla RT1 that only takes language as input, and what we call RT goal images, takes like a full goal image as input. So here, for example, you have this particular example of moving the Coke can near the green can with RT1, which works quite well, but also works really well with RT-Sketch. And then for the goal images, there's always something funny happening where the robot gets super obsessed with making it, as close as possible to the goal image, but typically due to general robot clumsiness, destroys the scene. So that's a very common failure case. Here we have, again, another example where the robot has to upright a bottle and place near the apple, where RT1 works quite well. RT-Sketch doesn't like to upright things, but at least it's placing it in the right spots, and the RT goal image kind of struggles, let's say. Okay, so overall, we found that actually RT1 and RT-Sketch compare favorably to each other, while RT goal images suffers typically from this excessive retrying error, where it really tries to obsessively align exactly the current scene. And I know I'm out of time, so I'm going to kind of skim through these examples. So here, for example, we have some examples where we see, again, how well RT-Sketch works if you give it like different levels of details. It works actually quite well. It works best with very precise edges, actually, we found. And then we have some examples where there are actually visual distractors in the image. And again, the RT-Sketch actually works surprisingly well, while RT goal image gets a little bit confused, tries to align colors rather than objects with each other. And finally, we have some examples where we tested for more abstract goals, like arranging these objects according to color, where we asked RT1 for very abstract instructions of completing the rainbow, where it gets really confused. And there's many more examples and experiments in the paper that is currently on arXiv. So what we found with this work was that it's kind of a first step to understand how a policy can be conditioned on sketches or on more abstract graphics. And they are really quite convenient for many tasks, and they can be very expressive. And it has 4 benefits. It's on par with language and images in straightforward settings. It's robust to sketch specificity, and robust to distractors, and also robust to language ambiguity. Okay, so today I showed you these two works on the topic of how to communicate manipulation goals to robots. The first one was purely based on language. The second one was giving you an alternative of just using sketches, which of course maybe later can also be combined with language. Priya Sundaresan is the first author of both of these works. She sits over there if you want to have more detail. And again, the kite work will be presented here at CoRL as well with a poster, I believe, on Thursday. And there are some interesting questions here as well that I haven't discussed at all. For example, it's still a little bit unclear, like when RGB images are better than other state representation. It seems maybe somewhat task dependent. And how do you provide the goal? There are all these different modalities. I think it's still unclear, like when, which one is the best. And in my lab, we often use manipulation primitives because they are much more convenient to train with fewer data, while of course feedback policies have their own advantages as well. So that's an open question. So thank you very much for your attention, everyone.
Hi. Any questions?
Yes, we.
Questions in the audience?
Oh God.
Yeah. From our next speaker, Zoe, we found very far to be this big day. Zoe is a city president of this world politics meeting. And one of the so these and Martin is areas of research specifically focused on the percentage of methods for sensitive processing and robotics, how the learning algorithms and related towards focus on the more focus on topics in these areas. If you're very interested in reading processes by learning, as well as really percentage. Thank you very much.
Great. I'll try to get over my jet lag today. Today I'll be talking about basically act, interact, and fine tune. So this loop that I think is going to be crucial to overcoming generalization and other problems, robotics. Okay, so really leveraging language models, vision language models towards a bunch of different robotics elements, including sensing, planning, and acting. And just as a shameless plug, I have an awesome LM robotics page you should check out that people have been doing a lot of cool requests updating it. So I thought I'd take this opportunity to really start thinking about kind of what do these language models and vision language models aid? So where do we improve and where do we still have issues in terms of actually having deployable robots? And so one way, of course, to think about this is through the standard sense plan act decomposition. Of course, sensing, sensors to observations has been, since the resurgence of deep learning, really improved significantly. And these days we have, embodied foundation models and so on. And so I think perception for pretty much any multimodal, conversion of raw data into features and observations is kind of in a decent state, although I'll show again, there's limitations there as well. In terms of planning, of course, language models are cool. You can ask them, fetch me a beer from the fridge, and they can decompose it into what are the sequence of subtasks that you'll want to do. One thing that this requires is world knowledge and common sense reasoning. And I think actually this was a big bottleneck in robotics because we didn't really know how to encode such common sense reasoning in a way that's not brittle and domain specific. Now we have language models. They pretty much know about everything that's available on the web. And then action, of course, I think is a little bit more difficult, but people have started to show that, transformers are great sequence generators, not just sequences of language of words, but sequences of actions as well, which is kind of cool. Of course, still a little bit earlier than the other parts, but still making a lot of progress. So I guess there's a question of, are we done? Do we just throw language models and vision language models at these things, and will they solve all our problems? And I think I'd like to argue that really there's a lot of issues that still remain, and language models typically bypass these issues, not really solve them. So of course, robustness and generalization is the big elephant in the room. Still handling kind of in the wild objects, environments, and in robotics, we have distribution shifts in policy space and also like task distributions and things like that. It's still really difficult. And so part of this difficulty comes from, of course, the lack of data. So often we take a language model, which I would argue, of course, has very large scale data and also high quality data. A lot of these companies have put a lot of effort into curating and making sure that the data is good to train with. On the vision side, I would say maybe it's medium scale. People, of course, scale to billions of parameters. It doesn't tend to help as much as it does in language. And part of this is, of course, quality of the data as well, where the diversity of the data is not necessarily kind of world scale diversity of imagery. But once we kind of put them together in vision language models, we often have generalization issues in the grounding, right? And now we need to associate language and vision. Of course, these days we have billions of pairs of images and text, but again, the diversity and the quality of that data is still pretty low. And then once you actually pipe it to things like embodied models or action, then the scale of data becomes really, really low. And what I would argue is that as we kind of progress through this, we're losing generalization. And so there's a question of how do we essentially get this back? And I'll talk about some kind of principles for this. Of course, the solutions that people are working on, there's a lot of great work on just scaling this up if you can afford it. Of course, you can try to get lots of real world robotics data. There's a chicken and egg problem here. If we want to get all robots in millions of homes, they kind of need to do useful things. In order to do useful things, we need lots of data to train them to do well at those things. Simulation is, I work a lot with Drew Batra and Meta, of course, and Habitat, and I think simulation can definitely scale this up. But I would argue algorithms and fine-tuning procedures and understanding how to actually take these models and adapt them to the specific domains that robots are using it for is really important. And I would argue one of the things that language really enables in order to get such data is interaction. So again, language is like a communication mechanism. And so we can interact with, as a robot, not just, people, but also even vision language models, right? You can take these vision language models, show them your sensor data, ask them questions about it, a dialogue, kind of this chain of thought kind of thing that's very common in language models, and really get feedback and data that you can then use to fine-tune your particular models. So kind of the thing that I would advocate for is this kind of really personalization. So of course, we should scale up robotics because that's going to improve performance. But maybe we should also look at things like personalization, where you have acting in some particular home or environment, and through interaction with not just humans, but again, it could be interaction with these great models, we get feedback, and then we fine-tune our models to that particular feedback. And then the robot can do well in the particular environments that they're actually living in. And so that's kind of what I'd like to talk about today, some works that kind of move us toward this, not that I've kind of solved or completed this loop, but kind of works that kind of push us on this front. One is, of course, just having benchmarks and data sets and simulation frameworks to understand how well are we generalizing. One thing that's, a little bit unfortunate, I think, across this large spectrum of work that's coming is that it's really hard across robotics platforms and environments to compare in a reproducible manner. So I'll talk a little bit about that. Another is, how do we actually fine tune in a way that doesn't lose our robustness and generalization properties? And that's something that I'll talk about, as well as kind of how to, again, deal with open world by basically gathering additional information, for example, through retrieval. So the first thing that I'll talk about here is benchmarks and data sets. And this is kind of led by Meta. I was involved as well. And Chris Paxton is the one leading this. And Sriram did a lot of technical work, but it's a large team. And this is a CoRL paper. So we'll have a poster today, both at this workshop at 2 to 3. So come here, and then in November 8th as well. So check it out. And where we started here is the Habitat 2.0 NeRPS paper. So this is a simulation environment. Habitat 2 added physics, while still maintaining very fast speeds, like tens of thousands of hertz, such that you can train reinforcement learning policies. And here we're doing something called a rearrangement task, where you're given, in this case, a geometric specification of start objects and their locations, and then you're given some goal objects and locations. And of course, the robot has to navigate to these objects, find them, pick them up, and rearrange them. So what's interesting about that is that the paper was showing that really reinforcement learning can do really well. This is actually just doing a pick skill, so just one subtask of that large long horizon task. But here we're training a reinforcement learning policy to do it. We're also comparing with classical methods like SensePlanX that use RRTs and point clouds and so on. And we also have privileged information where we, rather than give it point cloud sensor data, we just give it the raw point clouds that are, don't have occlusion and other issues. And what you can see is that reinforcement learning is awesome on seeing the data and objects and environments. But once we move to things like new, novel, unseen layouts, they degrade. And what's interesting is the classical methods, they plateaued earlier, so they don't do as well on scene, but they actually don't really degrade much. And of course, we could probably throw lots of engineering at this for a year and have it do really well on this domain, but that won't be general either. Then as you move to unseen objects, you get even further degradation, and unseen receptacles, the things that you're putting objects inside of, even more degradation. And now the classical methods actually do better. So this is to say that perceptual and policy generalization is still a large issue. And I would say, of course, this was, like a year or two ago, but this is still true even if you use like GPT-4 vision and all these other things. So what we did for this home robot is to take this and remove the goal specification, and rather than use geometric information, use language, of course. So now we have these language templates that you could say, pick up the picture from the drawer, place it on the serving cart. And you can compose this into object, start receptacle, and goal receptacle, and generate lots of data for this. And of course, we want to test this on open vocabulary. So we want to test it on completely unseen things in the world. So part of this home robots kind of benchmark and data set, and there's also a NeurIPS challenge, so you should check it out if you're going to be at NeurIPS. Has a lot of benefits. One of the cool things open source, there's a simulation component using Habitat, but it's also has all the software infrastructure for you to run on you put them on real robots. So I think this is a great, again, open platform, generalization, open vocabulary element, and actually in a reproducible manner. Set habitat synthetic scenes and 120 plus categories, so you can test both kind of instance and category level generalization, and plus receptacles. Modular framework, as well as one, that open vocabulary is through these lead detectors as well as clip. And as I'll show, they're awesome. And then there's newer ones that are even better. Sorry, let me share my screen. While okay, so here's an example of the robot kind of moving to a soap dispenser from the couch to the chair. So it goes to the couch, then it kind of picks up the dispenser, and then it moves. As you can see, it still has some issues with things like obstacles. So it kind of has to figure out how to get around it without bumping into things. But overall, it gets to the goal and then puts it down. So, of course, we have results, and we have done a bunch of ablations, so you should check out the paper and ask questions of the poster. But, showing kind of what if you have ground truth perception, like segmentation masks versus open vocabulary. And what you can see is that basically can achieve partial success. So here, whoops. Trying to get a laser pointer. So we can achieve partial success here, especially when we get ground truth perception information. Once you kind of want overall success, it gets pretty low. Once you throw, open vocabulary detectors, it gets even worse. So there's significant kind of issues because these methods just aren't that great yet. We also, again, you can take the same policies that you learned in simulation and throw them on the real robot, which I think is really cool. And so we test kind of, again, heuristic modular approaches as well as reinforcement learning approaches. So again, there's lots of imperfection here. If you notice, so there's a cell phone here on the counter. It doesn't really even pick it up. It's too small. Open vocabulary detectors don't pick it up. You also see the counter detector kind of flicker in and out. So again, when you're testing these things on Coco, that's awesome. But once you apply it to a real world robotics data set, then it doesn't work as well. So definitely check out the poster and ask lots of questions. I think Shriram and others will be here as well. So that's kind of, now that we have some edge to understand where we are in terms of generalization, I think again, one of the key things that I'm training on and hoping that it'll do well across everything, but really actually interacting with feedback, parse, natural language, great feedback from humans, but you can also do it so from vision language models. Again, these are VQA kind of models that you can show them your sensor data, ask questions, get feedback, and use that for fine tuning. Here's kind of an example that one of my students, Yusuf, did for a demo here at CoRL. So this is going to be, it's actually wrong on the slide. Sorry, it's Wednesday and Thursday in the next slide. It's going to be Wednesday and Thursday, but really showing you the power of combining vision language models with actual interaction. So here what we're doing is we're again doing this kind of finding objects kind of task. So let's say the robot is looking for something like a suitcase. However, there's nothing in the suitcase in terms of suitcases in the scene. And so what the robot needs to do is, again, leverage common sense to understand where should I explore to find this suitcase. So you can take this image and throw it to a vision language model. In this case, we use GPT-4 Vision. And sorry, I don't know, it might be too small, but it picks up all the objects in there pretty well. I haven't compared it in the open vocabulary like benchmark, but I suspect GPT-4 Vision is pretty good. Again, not perfect, but pretty good. So it gives you a list of all the objects that it sees. It can also perform reasoning, saying, well, given the things that I'm seeing in the environment, where should you explore next? And of course, it sees a bunch of clothing racks in the back, so it can know that it should explore in that area. And then it can actually give us an answer of like, where should we go next to find this particular object? Proof of concept, kind of looking at how can we use dialogue and exchange with, with the robot to improve its performance, in this case, for finding objects. One thing is GPT-4 is Vision only came out recently. There's no API. So we did a wrapper, but it's limited in queries. So what we did here is actually a simple solution, which is fine-tuned. So we took a ton of data, again, personalized data within our particular environments. We then generated kind of many image trajectories for this, generated dialogue exchanges where the robot was asking it questions to find particular objects. And then we did the popular thing on Twitter, which is for X to fine-tune using LoRa, in this case, a Lava vision language model. And then we apply it on the robot, and now we can actually do this without internet connectivity and limitations of GPT-4 Vision. And here, what we do is we take the answer from the vision language model of where we should look next in terms of what object we should look for. We throw it to an open vocabulary detector. Once we have a consistent detection, then we move towards that object and then do some policies to do some search around that. So here's kind of the entire loop here. So again, the robot is kind of looking for a particular object, like a suitcase. Again, sorry, I don't know if you could see the text, but it's asking Lava kind of, again, giving it the image and then asking it what objects are there, where should I go next? And then once we get consistent predictions from Lava, then it basically goes towards that and then again does like an exploration policy for that. Okay, and then it finds the suitcase. One thing is we don't really want to kind of evaluate this interaction. What model should we use? What algorithm should we use in the real world? Because the real world is hard. And so there's a question: how can we do this? Simulate this interaction. And so this is again work with Meta leading it. It was just released Habitat 3.0, which is basically a habitat with interaction in mind. And again, of course, the hard part is interaction with humans. So it has some really amazing human models of various diversities. Allows the robot to interact with the human in various ways. Let me see. I don't see unfortunately. Okay. I don't have a thing. Okay. One thing is there's lots of motion diversity on the human. So again, because of distribution shift, we want to maximize sim to real. So we want to add all sorts of different crazy behaviors that humans can do. And then we tested a bunch of different things in this habitat synthetic scene data set, including things like navigation by the robot following the human. So don't bump into the human or objects and things like that, as well as rearrangement. So how can you rearrange the environment in a collaborative way? And you can also have, again, in this notion of feedback, you can have human in the loop where you can actually have the human control either the robot or the human or both. So we can use this to gather a lot of data, again, to explore this interaction kind of idea. Okay, and so the last thing I'm going to talk a little bit about is a little bit more machine learning, computer visioning. And specifically now, maybe through interaction, we can get some feedback. The question is, how do we fine tune our models? We showed some examples where we do some lower fine tuning, but as people know, when you fine tune models to particular domains, you tend to lose generalization. That is, language models are awesome, or vision language models are awesome. You can ask them any general question. Once you're fine tuning them to a limited data set, they may not be able to capture all the kind of world knowledge, common sense relationships. And so there's a question that I've been interested in, which is how do we fine tune while retaining generalization? And this is something that we have some works on in computer vision. That is, we want to retain specifically out of distribution robustness, which these foundation models are very good at, when fine tuning to smaller downstream tasks. But eventually my goal is to kind of generalize this notion to other things, like how do we not lose in-context learning from language models, for example, when we fine tune. Again, all these things are known that we lose a lot of capabilities if we fine tune too much. And so the specific tool that we use to do this is kind of robust fine tuning through projected gradient descent. And this is something that's been done before. The idea is rather than just doing a constraint, you project it back to some ball norm foundation model. And so the idea that we're going to do is how do we do this for each layer of, let's say, or block of a transformer automatically without having a user have to specify which layer should I fine tune a lot or a little to not lose this generalization capability. And what we do is we use a bi-level optimization framework to do this. And you can see paper, it has a lot of cool theory of like why this is the right thing to do. Of course, with lots of assumptions, but you know, it does motivate the method. And so the idea is, again, you have kind of a multi-block or multi-layer neural network, and for each layer, you're deciding this gamma, which is like the constraint from which the pre-trained, you veer from the pre-trained model. So when you do unconstrained gradient descent step updates, you project it back to this constraint. And so it's a very simple bi-level algorithm just applied to foundation models. Really, it's just you do unconstrained gradient descent, you automatically tune the projection constraint using a validation set in this case. So this is the bi-level part, and then you project the new weights back on constraints. Shows a lot of great out of distribution robustness. So we fine tune only on in distribution data. This is called domain net, which has multiple domains like real and sketches and so on. So we only train on real, and then we see how robust is it on the other domains like sketches and clip art. And we see, unlike other methods, which actually sacrifice sometimes in distribution performance, we actually don't. We also have a follow-on on NeurIPS, so if you're going to be there, check it out. This is actually making it much simpler. It doesn't have the bi-level part, so it's twice as fast, and it uses all like some clever stuff my student came up with using mini batches of training from the previous iterations to get around this need for a separate validation step. Another thing that we can do to, again, increase generalization is if you don't know something about what you're encountering in that's out of distribution, maybe you should just retrieve new information about it. So we have this retrieval augmented methods where we take an image, we encode it through a clip image, and then we extract from a large text corpus the nearest text embeddings, and then actually funnel that into condition the model itself. In this case, we're doing what's called category discovery, like clustering of unknown categories, but you can do lots of other things as well. So I think I'm running out of time. I'd like to take questions. So in conclusion, you know, there's been a lot of huge advancements in large language models and vision language models and using them across this dense plan acts pipeline. I think one of the key things that we're still missing is generalization. And again, I think scaling things up will, of course, always improve things. At some point, you run out of data and your data diversity and quality just isn't enough to continue to push the performance up. And so that's where I think we'll really need this kind of cycle where the robot can act in the world, it can interact with models, it can interact with humans, get some feedback, and then do some maybe robust fine-tuning such that it can now do things better for the particular domain that it's in, while hopefully not losing a lot of the great, generalization that language models have. So with that, I'd like to thank my students who did all the work, and of course collaborations with Meta, and I can take questions. Thank you.
Thank you so much for the informative part. And I have a question about like how to like fine-tuning our model like during like we're also trying to like considering the generalizability of the model. So like do we actually have a quantification of like how well that our model after the fine-tuning like so do we have a like quantitative measure of like to understand, maybe we will be able to test like the fine-tuned model on the task we from the original foundation model, and how do we actually like well preserve the
Yeah, that's a great question. We kind of started in computer vision because it's easy. You have this notion of out of distribution robustness where you test, other domains that are perturbed and see how well it does. But I completely agree. Like, I think ultimately we'll wanna, that's why we, like the home robot benchmark, for example, specific a little bit more about generalization, which is generalization to new objects, new receptacles, and new environments. And so there again, you can basically, test, okay, when I fine tune, given some feedback, how much am I really closing in on the domain, and how much am I still able to basically handle things that are a little bit out of the domain and out of distribution and requires various reasoning. When you include language models, I think that's, evaluation, I think is a big like subfield of language models these days. How do you actually test robustness, generalization? What does it mean for like a general GPT model to be general? And people argue about this, right? Like, did GPT get worse over time? And we don't really have like quantitative benchmarks. So people are developing those, but I think, for, I'll let the language model people come up with those metrics, which we can of course use. But I think in the embodied sense, we can also test, again, generalization across all these things like object environments, and then even in the policy and task space, once you have complex tasks, like how complex can I make the natural language task and it can still handle it? Yeah. Great question.
With GCP study semi-supervised function, where do you see that you can benefit from like retrieving different modalities data? Like what other tasks would also benefit from CoRL for this?
Right. That's a great question. And yeah, of course, retrieval again in the language community kind of blew up around the time or a little bit before we were doing this. So I think, really the key thing is, again, updating the model to new data, right? And I think that can be, of course, like in the language model, it's like internet data. But I would say really what we want to do is have, again, these models on the robot. And you can even do, for example, retrieval of your context, right? Of the human. For example, a human has interacted with this robot over, let's say, a few months, which, pieces of information, when I ask it a question, which pieces of information from its past interactions should it actually, retrieve knowledge from to answer the question? So retrieval can be both from like World Web knowledge, which is kind of what we did there, but it can also be like used kind of as a memory, right? It's like a long-term, huge memory, for example, of past interactions and things like that. So yeah, I think there's I think there's all sorts of different examples. Usually it's when either new things come about. So like, for example, we were using the example of like the Apple, VR set or AR set. If the model knows nothing about it and a human asks about the robot about it, it'll have to retrieve some information. So yeah, I think there's a lot of potential, and it's not really been well explored in the robotics community for sure. Cool. Thank you very much. so much.
Okay, thanks so much. Oh, now, we're gonna move on now to some spotlight presentations from some pretty diverse. I'll go ahead and put the ordering on the screen right here, and if the speakers can all line up and come to the front on the correct order, that'd be really good. And also Google with Brian Richter. And yeah, his research interests are nowadays building intelligent embodied agents that can interact in unstructured environments by also leveraging VLMs and VLAs. So we are excited to be related to the research.
Thank you. Thank you so much for the introduction. Today, I want to talk about low-level embodied intelligence with foundation models. So why am I focusing on low-level embodied intelligence? Let's rewind back to a year. So if you have been to the first edition of the LangRob workshop, I did a demo together. And I was operating a robot in Mountain View, and Andy was doing the presentation here. And what happened there is the robot is trying to close the drawer and the finger fell off. And so the robot finger fell off, and then we did a live repair. We put back the finger back to the robot. And then the robot continues to finish the task of grabbing the bag of chips. So low-level manipulation is still a key challenge of robotics, and we haven't fully solved it yet. Now, on the topic of epic failures, let's take a look at a few more. So in this case, the robot is going to throw away the can, but we do have a motion of tucking the arm. In this case, if there is liquid in the can, it will drip on the robot and damage the robot. So we now need some more fine-grained understanding of our vision language models to give it such physical intelligence. In another case, the robot is putting the can into the sink. However, it accidentally turned on the water, turned on the tap. So the real world is just so complex. And how does a robot understand that it cannot do certain things, or what consequence it will cause by its actions? So these are all what I would summarize as low-level embodied intelligence. We want the robot to have this ambient physical intelligence. And so far, we have been using the large models for high-level reasoning. And how do we give them the low-level intelligence? So we actually went pretty far in using foundation models for robotics, and most of them are focusing on high-level reasoning and task-level planning. So we have been using language models as a general purpose planner. We have been combining it with affordance functions to make more grounded plan. We have been using language models to synthesize code and orchestrate a set of robotics APIs. We have been using it to do a little bit of low-level manipulation taken place, although it's not like fully dexterous type of manipulation. And of course, like we have been using language model as a user interface to communicate intents and corrections to the robots. Why cannot we make this a level deeper and use foundation models for low-level embodied intelligence? To me, there are a couple of challenges. The first challenge I would say is a challenge in data or a lack thereof. So large language models has been trained on billions or trillions of tokens. Palm has been trained on 780 billion tokens, and GPT maybe even more. So the robotics data is rather difficult to collect. So our team has spent about 17 months to collect on the order of magnitude of 100,000 episodes. So this is really like not on the same order of magnitude. So we cannot necessarily scale our robot data collection just like in the other domains like natural language processing. We will always be bounded by the robotics data, but can we scale otherwise? Can we scale by leveraging the scaling of other domains? To me, I think it's possible to scale with other fields. For example, you could have a solid foundation of text data or text foundation model, and on top of it, you add a bit more image and text data, and it's like building a cake. And then the cherry on top of the cake would be a little bit of interaction data just to align the action representation, for example. And that's what we have been exploring. I will tell you a little bit more in the later of this talk. The second challenge is like large language models do not necessarily have a low-level interface. So large language models are good at semantic reasoning, or their training corpora is basically text in and text out. They do not necessarily understand actions, and they don't have the action interface. Maybe we can find an action interface so that we can elicit knowledge from large language models. All right, so they do have some knowledge about motions and actions. So if you ask a language model how to make a dog stand up on 2 feet, it will give you something that is reasonable, like stand shoulder width apart, hand in the air. It's quite reasonable, but like they don't have the low-level interface to directly output the action or output the motions. So to achieve low-level embodied intelligence with foundation models, we're not there yet, but I think there are 2 promising recipes. So the first one is model consolidation, joint scaling, and positive transfer, which is to scale the robotics data with other domains, such as the vision language data. And the second is to develop a new interface of large language models. Let's zoom into part 1, model consolidation, joint scaling, and positive transfer. By model consolidation, I mean we can essentially, language model is doing high-level reasoning, and robotics is, some of the robotics tasks is low-level control. Now we can actually combine these tasks and combine the models so that we can maybe explore transfer between high-level reasoning and low-level control. After all, being able to do high-level reasoning, especially those are related to physics, will help you control a robot. Second is joint scaling, is to scale the pre-training of vision language models as well as scaling robot data. If we can scale robot data, that would be the best. But if we are only using limited robot data, maybe we can find a way to still scale. So I will show RT2 as a case study for how we do this joint scaling. And finally is positive transfer. Positive transfer describes the phenomenon where a model is benefiting from diverse joint training across internet scale language, vision, and vision language domains, as well as robotics domains. let's take a look at the model consolidation. So this is a progress of the Google DeepMind robotics team over the last 1 year or 2 years. So at the beginning, we have been demoed a couple of robotic systems from the Palm SEICAN, Palm E to RT2. And at the beginning, we need dedicated models for each module. For example, we are doing planning using Palm, which is a pure language model. And we have an affordance function, which is trained with Sim2Real reinforcement learning. And we have a low-level policy, which is using behavioral cloning of real-world data. And over time, we have been consolidating these models. We have been trying to find the commonality of these models. And one commonality is that they can all be viewed as a vision language task. Essentially, input is vision, and input is task instruction, and output is some sort of robot plan or robot action. And this consolidation enables us to basically do this, let's say, affordance prediction and planning in one model, Palm E. So we don't have to do this architecture surgery, which is brittle. And we can also just train on much more amount of data that both tasks are represented in. In Palm E, we haven't yet consolidated actions, so it's still just doing the plan and affordance. And finally, in the RT2, we are combining everything together. So the model is doing vision language modeling, but it's generating both the plan and action. All right, so to understand this a little bit more, we need to take a look at Palm E. So Palm E is an embodied multimodal language model, which we were able to achieve by fusing together Palm 540B and a vision encoder, which is a VIT22B. Palm E is trained on internet scale vision and language domain, and as well as robotics domain. So the end result is a powerful vision language model that performs tasks very well in vision language domain, but also it's able to control different robots to guide the robot to plan and do long horizon tasks. Palm E is one model that can do a lot of different things. So it can do embodied robotics tasks, vision language tasks across different, it can do robotics tasks across different embodiments and vision language tasks across different type of questions. The key innovation of Palm E is that we adapt a large language model into a vision language model. So Palm is originally a large language model, but we create these multimodal sentences where we can take multimodal data. The multimodal data can be images, it can be robot proprioception, it can be the neural scene representation. We just end up projecting these features into the same latent space as the token embeddings of large language models, and then it essentially form a multimodal sentence. You can ask questions like, given image, where image is then replaced by a set of multimodal tokens, and then ask a question as if you would do in a traditional large language model. It shows some very interesting capabilities. It can do, it is a vision language generalist, so that you can ask questions. It can do a little bit of instruction following. It shows zero-shot chain of thought for multimodal reasoning. But last but not least, it can do planning, task level planning for robotics tasks. So just to, yeah, I will show some robotics demo in a little bit, but what do you find that is super interesting and super promising in Palm E is positive transfer. So positive transfer is a phenomenon that I would describe as if you train your super large model only on your robotics domain, it is not performing as well. It is essentially overfitting to your robotics domain, but it benefits from leveraging a large amount of data from other domains, like from the internet scale vision and language domains. So we have tried to train Palm E on dedicated robotics domains like 3 tasks, task and motion planning, language table, and SEICAN, and the performance of 50%. However, if we trained together on all sorts of domains, including the robotics domain and also VQA type of domains, it tends to perform much better. The performance is close to 100 in 2 of the domains. Right, so this shows that using internet scale vision language data, you're seeing this knowledge transferring from like understanding images to helping with robot task planning. Another hypothesis is that maybe using the internet scale data is a regularizer for your robot planning module, like so that it doesn't overfit to your specific domain. So I'm gonna quickly show some results of PalmE. So using the PalmE as a task planner, it can understand sequences, it understands human instructions, and it can do a long horizon task despite human intervention or our adversarial perturbation. So this is the same kitchen where the robot finger falls off. Now the task is to grab a bag of chips for the user, and the robot is using PalmE to plan. So this PalmE model understands both task planning and affordance. Now, I am messing up with the robot here, so I just put the bag of chips back. The robot understands the task is not finished yet, so it like continue to repeat the step to take the chip out of the drawer. Now, I didn't mess it up with anymore, and then it would just close the drawer and continue with the task. Interestingly, we can use the exactly same model on another domain, which is language table. It can arrange blocks on a tabletop setting. And this is entirely the same PalmE model. It sees different images and it snap onto different tasks, and it will output in different ways. So this is one model that is not doing vision language, but also robot planning for different embodiments. This further inspired us. Now that we can do this positive transfer in this robot planning domain, can we go even a little bit deeper? Can we leverage web knowledge to do low-level manipulation? Because that will unlock a lot of new capabilities for robot motion. Because as I mentioned, low-level manipulation is still a big challenge. So that's why we presented RT2. So RT2 is a vision language action model. So here, instead of generating plan, we're generating actions. And it shows that it transfers web knowledge to robotics control. So one example is that you can ask the robot to pick up from a pile distinct animals. And from that single instruction, it is able to pick up a dinosaur. So it's able to do this one-hop reasoning. That distinct animal, in this case, is dinosaur. And from the dinosaur, it's also able to generate a sequence of actions to fulfill this task. Right, so how do we do this? So as I mentioned, we are consolidating different models, and now we want to use the same vision language model, not only to do planning, but for low-level actions. So we just need to fit our data to a vision language model training recipe. Fortunately, we have been using RT1, which is already quite similar to a vision language model. So RT1 take as input a language instruction, an image, and it output actions in a tokenized manner. If we zoom out far enough, it's actually a vision language model, right? The only difference is that they are with different output tokens. So in the RT1, we're using a dedicated set of output tokens, which is not necessarily compatible with language. So we just need to find a way to serialize the RT1 tokens and then basically represent them as a language or text. Then we can basically treat the RT and the vision language model interchangeably. So we did it quite simply. So we basically represent the actions in an 8-dimensional vector. They represent termination, condition, and position of the delta position of the end effector, delta rotation of the end effector, and the closeness of the gripper. Each dimension is discretized into 256 bins, so you can represent them with a number from 0 to 255. So it's really brute force, but it actually works, which is a simple design. For example, this sequence 127, 115, blah, blah, blah. This is actually represented action. It represents a delta motion in the end effector. And we can just use such text to be the output representation, and vision language models can be trained to output such representation. This also touches upon my comment of like large language model don't have a low-level interface. So this is a way that we artificially create a low-level interface where we force it to speak robot language. We force it to have a low-level interface. We have tried other alternatives, such as float numbers. It turns out the tokenizers are usually not super float number friendly because there's decimal points. We also tried human language left or right, but it's more semantic than it's numerical and cannot be directly executed on a robot. So if we just commit to this sequence, integer number as action representation, then we have a vision language and action model. We have fine-tuned different vision language models to be the vision language action models. We have a procedure called co-fine-tuning. So we have already established that fine-tuning on a large diverse domain usually helps, and it prevent the model from overfitting. So we just keep the original training mix of VQA, captioning, and other tasks together with the robot training data. So we call this procedure co-fine-tuning. And in our paper, we showed co-fine-tuning is better than just a fine-tuning on your robotics domain. So in theory, this robot can pick up a code for you and tell you a joke at the same time. We pre-trained on web data and a bunch of robot data, which is exactly the same as RT1. So if you think about it, in RT1 to RT2, we didn't add the robot data, but we improved generalization significantly by leveraging internet scale data. So at the inference time, then we would just tokenize the input image and tokenize the language instruction and treat it as a visual question answering task. We would just ask, what action should the robot do to achieve a certain task? And then it will output these 8 integers, and then it's detokenized into a robot delta motion. The robot executes the delta motion at a frequency of 3 Hertz, and then it samples the next observation. So this is just a loop, and it will do this over and over again. So what will happen if we fine-tune a web scale vision language model into a robotics domain? It inherits a lot of knowledge about the visual world. It understands a lot about the visual world. So we test it in a very interesting way. So we test things that it has never seen in the training set. So, and we strictly test on the emergent capabilities. So previously, the robot has seen a lot of objects. So to make sure it hasn't seen the objects, we will actually need to run to the dollar store and buy some new objects to make sure it's not leaked in the training data. We test a couple of capabilities, such as understanding symbols, understanding flags, and some like reasoning tasks, which I will talk in a little bit. But as you can see, the robot is able to perform many of these tasks just out of the box. So these are pure generalization performance. We also, so in the large language models, there is a procedure called, there's a prompting mechanism called chain of thought prompting, which elicits reasoning. So we were wondering if we can do the same with a large vision language model, a large vision language and action model. So this is not completely zero shot. So we actually fine-tune the model to generate chain of thought. So instead of directly generate actions, we would first generate a plan. So given a high-level task, we will generate a plan, and then it will generate the actions. So we fine-tuned it on a couple hundred synthetic examples for a couple hundred steps. So it's in between of a fully fledged fine-tuning and in-context learning. And we find it can do very interesting things. For example, if you put a rock, a earphone, and a sticky note on the table, and you ask, I want to hammer a nail, can you help me? And it will say, I will pick up the rock, and then generate action to pick up the rock. So it does this high-level reasoning and low-level control in just one model in a single decoding loop. Here are some examples of the chain of thought reasoning. So you can ask it to pick up the object that is different from all other objects. So it requires really nuanced visual understanding. Yeah, so As a summary, we propose vision language action models. It significantly improved generalization over our previous robotic transformer work. It generalized to new tasks and objects and exhibits chain of thought reasoning. It shows that improving underlying model and then joint training with internet scale data can improve robot control and generalization. Capabilities. I would like to, so in RT2, I mentioned that we can get a lot of bang for buck by not generating more robotics data, but taking in data from other domains. But if we could generate more robotics data, then we can do even more. We can jointly scale robotics data and vision language data. So that's why we have the RTX initiative and open embodiment. Open cross embodiment. So you'll probably hear more from other parts of the CoRL. But one thing that I want to point out is that we also see positive transfer there, that model trained on the diverse domain outperforms domain-specific models. Like when you mix all the data together with co-fine tuning with the vision language data, it actually performs quite well. As a summary for this part, we did model consolidation. We can now do high-level reasoning and low-level control in just one model. And we see promising recipe of jointly scale the robotics data and internet scale vision language data. And we see positive transfer helping us to build more generalizable and multitask type of robotics models. Now I want to switch gear to new interfaces of large language models. So large language models, as we have already established it, if we kind of force installing a low-level interface to it, such as RT2, you need extensive fine-tuning and the data curation. Can we do it to zero shot? Can we mine a little bit more what it already has? We found Reward to be a really good interface for large language models. Large language models can write code, and the Reward is a very general representation of a task, of a motion, and the people in the reinforced learning literature have studied it extensively. And so we propose language to reward for robotic skill synthesis, which is also being presented on Wednesday, I believe, as an oral presentation. So large language models they understand a lot of motions, but it's not executable on a robot. Large language model do not quite understand, does not directly write code to control the motors of the robot, because that's a little bit difficult. So can we leverage the first part where it understands the low-level motions and find a robot-friendly way to communicate to our embodiment, right? We have been thinking about what is the best interface between language and low-level actions. So I believe the audience here are all using, for example, language model to help writing code. So I bet you are using Python instead of assembly most of the time. So you are not using large language model to directly generate assembly code or machine code. So we can draw some analogy here. What would be the Python of like language and robotics? We think it is reward functions. So reward functions is a rather general interface. It is very expressive, and a lot of things can be represented in reward code. Unfortunately, language model has read your reinforced learning textbook as well, so it can also generate reward code. We use a mechanism called reward translator, which is a large language model to generate the reward code. The reward translator has two parts. The first part is a motion descriptor. So there's still quite a large domain gap from your instruction to a set of reward code. So we plan to bridge this gap in a two-step manner. So first, we generate a motion description using a templated language, so that it basically tells you how the dog should stand up on 2 feet in something similar to natural language. And finally, when you have a more structured representation, it's more structured, then it's easier to generate the reward code. It's an easier translation problem to have. they are actually just the same language model with different prompts. So this can be achieved by prompt engineering. And after we have the reward generated in code, we use a motion controller to directly optimize for the motion. The reason that we are doing this is that we want this process to be really interactive and the user can be in the loop. RL, as previously being presented, it can be pretty fast. It can be hardware accelerated, but the motion controller that we're using here is even faster. You get the motion in real time. And it will optimize for low-level actions, and then we execute it on this simulated robot. For the motion controller, we're using Majoko MPC. It's a black box optimizer. Given it a set of cost functions, which you can just flip the sign of your reward, you can basically use a Majoko MPC to optimize for the motion. And it's a sample. You can use sampling-based optimizer so that it can break contact easily, so it can generate really diverse motions to solve the reward function. To demonstrate how well our system works, I will give a couple examples. So first, we could say, make the robot stand up on two back feet like a human. It generates reward functions just fine, and we optimize for the motion in real time, and the robot is standing up. Now we can be a little bit more ambitious. Now we can say, make the robot do a moonwalk while standing up like this. So it really need to understand what is moonwalk. And it doesn't do it quite well. It generates some motions. Fortunately, we're using a large language model, and the system is coachable in a way. So you can just explain nicely. Moonwalk means the robot should walk backwards while the feet swing forwards as they're moving forward, and you can correct the code. And then the reward translator pinpoint where are the errors in the code, and then generate a correct set of code and do a moonwalk. We can also do it in a multi-step manner, like you can ask the robot to open a drawer, put the apple in the drawer, and then close the drawer. Like they can generate different stages of the reward to accomplish a long horizon task. Right, we have compared with a baseline, which is code as policy. We have also compared with just generating reward code without generating motion description, and the performance is a little bit worse. Finally, we are also able to transfer this to the real world. I will skip some of the details, but just to show that you can use the language to reward systems to synthesize reward, and using MJPC to optimize for the motion, and then it works for the real world. There are some interesting follow-up works. Some of them are also being presented in this workshop. One of my favorite is Eureka, which brings the language to reward to the next level, where they have the reward reflection and the mutation, which makes this process a lot more automated. And they showed that in some of the tasks, it outperforms language to reward and achieves human performance. So I'm gonna skip this part. So for the new interfaces we established, we can use the reward as a bridge of large language models to low-level control, optimize for it in real time, and the output it outperforms than generating action directly or calling like action APIs. It's a much more flexible interface. So I would like to summarize my talk by saying that we have been exploring on how to use foundation models for beyond high-level reasoning for low-level control. I believe we're just barely scratched the surface of it. So far, we found a couple of recipes that has been promising, which is to co-fine-tuning it with large-scale vision language data. Another recipe is to develop new interfaces of large language models, so you can do this transfer much more easily. And there are still some open questions going forward. Is that currently we show that large language models can generate new motions. It can do some generalization. It generalizes very well actually in the semantic world, so it understands what is a German flag. And can we generate new motions? Can we generate a twisting motion, for example, just by giving it the word, giving it the instruction? We also have seen some signs of life of the transfer from internet scale data to robotics data. I wonder what is the limit of that? Can we get more transfer from internet data to robotics data? What is the ideal mixture of robotics data to internet data? What is the right media? Is that videos, or is that assembly manuals, or some like tutorials? Or egocentric videos. It's not super clear what is the best way to transfer internet data to robotics. And I think we can figure out this together and further improve using foundation models for low-level actions. And with that, I would like to thank my colleagues for doing this amazing research, and stay tuned for more. Thank you so much.
Thank you very much for a very nice talk. We have time for one or two quick questions while we set up our next speaker.
Hi, my name is Johnny Bond. I'm a student at UNC. I'm studying robotics. I have a question with two parts. So I look at your RTM1 and T2RDX formalization, and I think that when you talk about low-level actions, you're actually talking about so that the finite like the action totals are actually this X, Y, Z and rotations of the and the factors or things like that. My first question is, do you think that for the audit is like going now to like is it low enough? Are we just talking about positioning control? For example, if you just talk about positioning control, does it really solve the question like in your video, like you said, like you crash your lookout quick in your first demo videos, right?
Right.
Does it really solve that? Second question also related to the model architecture. When you talk about internet data, right? We usually have more like 2D egocentric data, but all of them almost 2D. But you're talking X, Y, and how do we think like basically close that gap? Or and can we just use the internet data, or do we really need more 3D data?
Yeah, that's a super good question. Set of questions. So for the first question, it's about action representation. So far, just for simplicity and just for kind of being able to represent a lot of tasks in the same way. So that's why we're using just a positional control. That's rather a practical decision, right? So you can represent a lot of different embodiments using the same set of representations. So that's why we're using this for now. I believe it will be a very fruitful direction to do a little representation.
Great, thanks so much, Faye. For our next speaker, Nathan Lambert will be joining remotely. So quickly introduce Nathan. He recently left Hugging Face, is now with AI2. Before that, he was finished his PhD at UC Berkeley, where he was advised by Professor Christopher Pister in the Berkeley Autonomous Microsystems Lab, and pseudo-advised by Roberto Calandro at Meta AI Research. He's also my good friend, and I really enjoy his newsletter, Interconnect AI, and his podcast, The Retort, as well. Anyways, I'll go ahead and hand it over to you, Nathan. Could you do a quick audio test to make sure we can hear you?
Yeah. Can you hear me?
Could you say something?
I'm talking. Let's see what this is set up as. I can just try to. Is this better? Try to kind of yell at my computer.
I think we're good.
Yeah.
Try to screen.
Okay, I'm gonna get going. You can send me messages in Zoom or interrupt because there's kind of synchronous problems when you're doing it remotely. So thanks for having me and putting up with this. I think this talk is hopefully going to be a little different than some of these. I'm talking about bridging reinforcement learning from human feedback kind of back from the LLM space that has been developing into control and robotics. And listening to the previous talk, this is obviously something that people are thinking about. So hopefully this can foster discussions that I kind of wish I was there for, but you can let me know how all of these go. And kind of just thinking about reinforcement learning from human feedback a lot now, it really represents an interesting kind of focal point of the community. So here, this is a meme that a lot of people will show you. It's referencing a Shoggoth monster, which is from like a Lovecraftian fiction. And it's really a monster that is underneath everything that can have a kind of happy face on it. And that's what RLHF is representing right now, which is this little bit of technology, which is tweaking language models or tweaking large machine learning models and making them a little bit easier to use and potentially seem very different than what is actually underlying them. And there's a lot of bigger issues in AI in the world right now that are kind of heating up, and RLHF is a focal point for how people understand this technology. So I'm really interested in trying to figure out how to expand research directions in RLHF and bring a lot of people into this process. That's very important. So I don't think, given this, everyone knows what RLHF is now in terms of what it means, but we'll kind of talk about what it is and then how to link a few different fields and ideas from work spanning kind of different eras of my life to show how people can work on this problem. So if we start with the basics, I think most people here should know this. Reinforcement learning is a trial and error learning method where an agent acts in an environment. There's states, actions, rewards. And then things kind of get a little bit different as you transition this into language, and then you transition into this RLHF framework. So in language, what we're doing when we're approaching RLHF, what we're doing is that the agent becomes a language model. The action becomes a string of text, which is a completion to a prompt or a query. The environment becomes really limited because the environment ends up really being something like a reward model or some other. If you can have a human in the loop, great, but that's really rare. So the environment is limited. And the states are really prompts. So it's pretty different than thinking about this from the robotics perspective, where the states correspond to actual physical motions and things like that. And then zooming in RLHF, the kind of feedback loop of RL is broken. So this it's not really a continuous feedback loop. What happens is you sample one prompt and then you do one completion, which I kind of talk about as being one action per sequence. And this state distribution, so the prompt distribution, will be really different than something if you're going to do like a simulated task in robotics. Like the distribution that these prompts can come from is really broad and not that well characterized. You don't really know what your initial state distribution is. And then because there's this one action, there's really not the notion of long-term reasoning and credit assignment that reinforcement learning is known for. And a lot of people talk about RLHF as being a bandits framework. And it's just important to kind of understand why. And this is implicit in a lot of the experimental details and how people actually try to deploy this later on. And where I want to start talking about RLHF, which is that it actually came from kind of the decision-making field rather than language models. Before deep learning, there was something called the tamer, which is manually tuning a reinforcement learning agent with human feedback. So what they did is that they showed a human the environment, and then the human labeled scores, scalar scores. So the humans kind of acted as the reward function to show that agents could still solve tasks where humans were kind of an intermediate member in that loop. And then the popular paper is this kind of Cristiano et al. Paper, which I'm going to go into a little bit more detail because I think the results are very compelling. And what they did is they compare trajectories, and they have humans compare these trajectories, and then they can train a reward function based on which trajectories are preferred and completely ignore the environment reward. And then they use this with existing deep RL algorithms to get pretty impressive performance. So I'm going to zoom in on this more because I actually was just studying it more deeply for making this talk. And this, to me, the results are actually pretty profound. And I'm surprised that we don't see more work with this method and following on directly. Maybe we do, it's just not described in that way. So they don't have access to the reward function. And the evaluation suite is pretty standard for deep RL algorithm papers at the time. There's a set of simulated tasks with different dimensionalities and different challenges, and they baseline a few different RL algorithms. And kind of the core result is that the human labels, where the humans are just qualitatively choosing which trajectory looks better for solving a task, often actually worked better in the results than the synthetic data option, which is if you have two trajectories, the trajectory that is synthetically chosen would be the one with a higher reward from the environment. So there's something even in this simple domain of simulated control where the humans were kind of nudging the model in a more interesting direction than the default reward functions, which I just think is worth expanding on. And if you go into the paper, this is kind of the core figure that shows this. So only like two colors to really know. Orange is the RL algorithm, which was A2C or A3C, I don't remember the exact acronym, which was the normal RL algorithm. You run it in the environment, Walker, Hopper, these are fairly standard. The three shades of blue are this kind of synthetic data that I talked about. And then the purple, which is best highlighted in like ANT, is this human data where the humans are comparing the trajectories and they train a reward model on that, and the RL optimizer optimizes that reward model. So back in 2017, I think that's when I was starting my PhD. It's safe to say that the deep RL infrastructure and know-how was much less sophisticated. And given what people are doing now and kind of the numerical understanding that's developing, I would really like to see like what can we do with these types of ideas now when people are tackling much bigger tasks with RL. So this paper is still really relevant 6 years on, which is pretty great. And this kind of serves as the foundation to what people are doing in RLHF for language models. So if you really high level summary of what people do for RLHF and language models, most of the talk is abstracted so that it is not crucial to understand all the details. What people do really is that they have some base model. You'll hear terms like instruction tuned, a helpful model, a chatty model. And that really just means if you type something in that's like a query or a question, it'll give a reasonable response. They take that model, they collect some preference data from some GUI, from user applications, which really just means comparing two answers and which one does a human like better. They use that to create a reward function with another language model. And then the RL optimizers that we know and love, they make that reward function go up, and the language model behaviors change in a qualitative manner, mostly that makes them much easier to use. This domain sounds pretty high level, and that's really how it operates. There's a lot of data processes and things, and the specific mechanisms and any sort of causal understanding is not that well understood for RLHF with language models. It's very experimental still. So from kind of here, I'm going to take a step back and kind of interweave two topics that I've studied for model-based RL and RLHF, which is kind of the idea of when you train modular systems with multiple machine learning models that you're training, you can get something called an objective mismatch, where you have to figure out how to synergize these different models with each other. So this is kind of taking a step back to model-based RL. And if we think about like model learning for control, the origins did have a pretty specific goal, which is like, we look back at classical control. There's something called system identification, where the idea was if we can learn a global model of the dynamics of the environment, we can then learn controllers that solve any task that we want. And you can take these things called elicitation trajectories that cover the state space, and you know that you're getting correct coverage to solve the task. In reinforcement learning, data collection looks really different. So we kind of do these iterative tasks, and then you learn a model that mostly covers the distribution where your agent is interacting with the world. So then if we kind of take this into the model-based RL loop, what you're doing is you have this feedback loop, and the only change is that the agent normally has a structured learning of the dynamics, the transition function within the loop. A lot of the other components look similar. I would say in RL now, model-based and model-free algorithms are kind of converging, where people want to take the best of both worlds from each of them. And that's great. I think that's what you should do. But you're just learning this dynamics model center, which is a parameterized function, et cetera. And then if we kind of take these two slides with the origins of model learning and what model-based RL is doing, we kind of have this key assumption is that if we're maximizing the accuracy of our dynamics model, that's going to be correlated with task performance, which is through this kind of episodic reward. And then the question is like, does this actually hold? if we revisit the model-based RL loop, it's pretty clear that we're not training policies to do this directly. So if we have a policy in the world, it'll interact with the environment. This will get some response data, which is the form of trajectories, which is state transitions and reward. And then in model-based RL, most of the algorithms that I was training during my PhD, what you then do is you take the state transitions, you train a dynamics model for maximum accuracy, and then you use that for control. And kind of the idea of objective mismatch here emerges as that fact that we aren't using these reward signals to actually train the dynamics model and the policy across most of the algorithms that we use. Without going into a ton of experimental details, what this essentially looks like is that you can get a dynamics model with really high accuracy, but actually performs with low reward. The intuitions behind this, which also applies in things like language models, is that our losses are built on means. And if we're taking an average over a full batch, the one action or the one word that we need to be really accurate could actually be modeled really poorly, and then the average is covering that up. And I've seen that in dynamics models. It takes a lot of hand-holding into the weeds to actually show that, but that's kind of the central vision of like what we need to look at when we're looking at these models to figure out if they're actually correlated with what we want to do. So what this looks like in practice, if you actually encode these, you end up with these two equations, which is the left is training a dynamics model for accuracy, or repeat theta is your state transition. And then on the right is control, where you're taking the expected reward over a policy with something like MPC or policy gradient algorithms, whatever it is. And this is what we call an objective mismatch. If we then transition back into RLHF, this is where things get a lot more complicated. If you're going to try to take an origin slide of optimizing human preferences, I think if I was in the audience, I would almost ask for questions now and like, what do people want to put on this slide? And some of the answers that you would probably get is like operant conditioning from like studying animals in psychology, von Neumann-Morgenstern utility theorem, and a bunch of economics, the history of RL with Bellman updates, blah, blah, blah. I've worked on a paper to kind of put all this together, like what are actually the origins of human preference. We studied everything here, but like there is a ton that goes into the motivating theory of RLHF when you compare it to something like model-based RL, which kind of followed an intellectual, it kind of followed a linear path to model-based RL from a few methods coming together and working. RLHF is a lot more complicated, and we kind of see this in the notion of objective mismatch, where you get between a reward model and a policy. So if we were kind of try to squint and set up the same argument for reinforcement learning from human feedback as compared to model-based RL, the intuition that most people start with would be that if we increase the reward model score, this kind of score we're getting from human comparison data, it would correlate to some notion of language model performance. And this kind of would look like in practice is you like look at the rewards you're getting across some sequence of tokens and then or sequence of responses. You correlate these with various language model evaluation tools. There's things like MMLU, which is a reasoning task. There's a lot of other things like ELO rankings, GPT-4 rankings. Like people are using all sorts of stuff to evaluate language models now. And the question is, would this actually be correlated with the performance of the model and what users actually want? So if you actually train RLHF, in practice, it is very much trying to get the reward to go up still. So there's a bunch of plots here. These are example plots from at Hugging Face where you're kind of looking at the reward you're getting from the environment and the PPO loss from the optimizer. And it's like, what do we actually do here? We're trying to get the reward to increase, but there's a lot of engineering challenges in the way, which is like GPU memory. How do you tune RL with a large model compared to the policies we all learned with it? Dataset formatting could be a huge issue, because it's probably one for robotics as well. And kind of the long story is that like these runs can fail for all sorts of reasons. Like there's unstable hyperparameters, which is the blue, which looked like it was going well and ended up scaling. There's hyperparameters that just don't really have any signal. You can do these language models have really interconnected software stacks. So like it can be going well and then you can get broken by a Python version. And then eventually you just have a stable version. Sorry, I'm in a meeting room, it's heating up. Okay, so what you get in RLHF is that you kind of have this view of RL where the feedback loop is a little bit broken. So this is very similar where your training data is this distribution control, you get a prompt from it and your agent responds and you send it to the reward model, which tells you how to actually update this other language model, which is your policy. And all the meanwhile, you're outputting various scores to measure evaluation tools. And one of the ways objective mismatch kind of arises in language models is that we don't really even know if a higher reward from the reward model is going to be linked with their evaluation metrics. So there's kind of two things that we're designing in tandem, which is the reward models, the evaluation. We're also figuring out how to link all of these with RL, which anyone that's worked with RL knows that that is kind of a big ask. So then if we revisit this, I presented a kind of simplistic view of way you could view objective mismatch in language models, but in reality, there's a lot more questions, which is how do you control your training distribution for the reward model versus the prompt you're using for RL? It's kind of like this problem of your state space can change between your like environment and then what you're actually providing to the environment because you control that in RLHF. It's not boxed in like a robotic control problem. And we don't actually know if language models can represent the policy we want with human feedback. There's a lot of concerns if evaluation is even conceptually correct with language models right now. So these are all things within scope of what it means to do RLHF well. And we kind of need to address each of them individually rather than focusing on one individual metric, which might lead to problems in other places. Some example ways where language models might be like misusing RL. Two things to note. The more popular one is probably on the left, which is a representation of the chat refusals from Llama 2, which is in the appendix. Essentially, as they add more like harmless data to the training mix, the model refuses way more prompts that it shouldn't in general conversation, which people have seen. There's the famous example of like, how can I kill a Linux process, which the model wouldn't answer. And then there's on the right is an annotated version of the GPT-4 report where they show evaluation scores before and after RLHF, where green indicates a improvement, that's what I added, or red indicates a decrease and no marker is similar. And really RLHF doesn't drive the evaluation tools, at least OpenAI reports. And this is important because it's like not fully about performance, but rather about kind of qualitative understanding and evaluations in this language model space. That's not necessarily true for control and other things. So if we kind of compare these, this is where the talk starts to draw back towards robotics, is what is the difference between the mismatches in model-based RL and RLHF with language models, and what can that kind of tell us about open questions for research? Model-based RL is really a much more defined work stream and evaluation stream. So what your environment is, it's giving you a reward function, and that reward function is really the driving metric behind your research. That's what implies like a good agent or a good new algorithm or something like that. With language models, we are building our own reward function, and they're often not shared publicly. So there's a lot of ambiguity in like what a good reward function is and what your reward model should be doing. And with that comes a lot of experimental challenges, like the large state space, large action space, how you've kind of hacked together your RL algorithm to work on just one-step processes and many other things. And then if you kind of cast robotics, I see that there can be some things in the middle, especially when you're working in the real world, is that a lot of robotics problems, we're actually designing the reward function to try to help the robot learn a behavior that we want. So there is that human in the loop factor in many different ways. And similarly, like the distribution control is not as good in the real world where resets are very costly. Things might change over time. It's not this kind of sandbox where you can throw a ton of compute at it all the time. But there's still a big difference where robotics, I think you can focus on a specific task much more than you can with language models. With language models, you're expected to make everything better when you're doing RLHF, and that makes it really hard to understand the methods, because if you have a specific endpoint, you could just try to improve it and understand how that kind of human feedback comes into play. Okay. I'm going to kind of go through some conclusions. I have plenty, I'm good on time. And kind of continue in this theme of like, what are opportunities to work in robotics, and what do people like me want to work on, so the things from robotics that could then be translated back into language model research and kind of get a synergistic feedback loop to understand what these methods are actually doing. So as a kind of starting point, I wanted to list some of the things that people working in RLHF will think about, and like, how do we actually make models easier to use for humans and accomplish this kind of ambiguous goal that we have in making models easier to use and more steerable. So this is roughly sorted. It's not what everyone would think. It's kind of my recent check-in. And the first thing that comes to mind is data quality. It's still driving almost all of these investments. You hear a lot about the wealthier companies having tons of people behind the scenes creating data. And then there's also the more open source or academic side of things, which is using synthetic data. GPT-4 is generating tons of data for reward models and for actually just doing supervised fine tuning. It is a great engine, and people are getting a lot of performance for that. And if there's other ways to do that, it's great. Base model capabilities, a lot of rumors that RLHF doesn't work without certain capabilities. It's like, does that translate to other domains? Is that just a language problem? Regularization is really important to kind of integrate this human data into the language model. There's things like KL constraints to make sure that the language doesn't become gibberish, and it's really preventing the exploitation that reinforcement learning is known for. There's a lot of experiments with simpler rewards like sentiment classification rather than just like relative performance versus ChatGPT, which is extremely vague. And then also there's things like simpler methods that people are coming out, both in simpler to implement and then maybe even simpler to like understand. So there's direct reference optimization, which is really popular from Stanford, which is just a different loss function that doesn't use these kind of process of learning a value function that DeepRL is known for. And then Llama 2 kind of quietly talked about rejection sampling, which is just filtering your data set based on ones that seems like high reward, and then using a simpler method like just the autoregressive loss function to update the model. Then I kind of went in and I went with quick takes to figure out what these would mean in robotics. And if some of these are wrong, take that as a motivation to actually work on this and tell me that, because I haven't been kind of been in and out of robotics. I was in robotics for a long time with PhD, and then at Hugging Face wasn't really, and now I have more of an open agenda that I can talk about these things. And I think that like data quality is hopefully the flywheel is going with robotics. RTX is probably one of the most excited moments I've been for robotics in recent times. And that kind of sets the precedent that people can create human data and preference data across trajectories and share it with other institutions. So that's really exciting. I then put base model capabilities, and I crossed this out, but I actually, in my talk, but watching the talks before, I think that some of the work that like Google Brain is doing in these multi-institutional efforts to train large models for control and control understanding are actually warranted to as a point here, where if you just kind of integrate some of this data and these human feedback methods into those, like what types of behaviors are you seeing? Just copy the methods from language generation, apply them to control, and see what we see. I think regularization is a well-known problem in robotics. It's like you don't want your robot to break itself. You don't like there's certain physical realities that you don't have in the simulator, and then you are used to trying to do these things. And then this is kind of where this starts to unravel. I don't have as good of answers, but like if there's simpler rewards that you can use, which is other ways to compare trajectories other than just human labels. So I think there's examples in like the image domain, which is like how compressible your image is. It's any, or in code, it's like, does your code run or not? It's any metric where you can automatically compute a quantitative score from your kind of data that might be different than the actual task, but is related to the performance that you're interested in. And it's kind of this way of integrating other qualities into your training process that may have seen and may not have seemed possible in the past based on this kind of comparison structure. And then the methods part is kind of a point of this workshop. I think the talk before, and then I know Dorsa's on a panel later. And this is something that people are very actively working on. And that's kind of what I've been studying, making this talk, and why I'm interested in this workshop. So then kind of a few this is the pointer slide to the fact that in reviewing this, there are big gaps in the language model literature for RLHF, which is like inverse RL, which is the subfield of reinforcement learning about learning rewards from agent behavior, isn't really represented in the language model literature for RLHF at all. And like, I'm very confused by this. So hopefully you can tell me where people should start there. And then there's recent works in robotics where people are doing a lot of things about learning reward functions from behavior between demonstrations and kind of learned behaviors. There's this inverse preference learning ideas that I think Doris is at the workshop, and then a lot of other things I've seen from recent works that are well after the things in the introduction, which are hopefully being discussed and expanded on. And that's kind of what I'm continuing to study as I try to figure out how to propose the ideas for bridging these very related research areas. So then to kind of conclude with the opportunities that I see for impact in this field is like, if we figure out how to integrate human feedback and data engines into robotics, like what is that going to mean for the growing field here? And to start with, the kind of grounding of RLHF methods for language models, I think that the robotics people, and a lot of them are actually building RLHF, a lot of the reinforcement learning and decision-making people are now doing this language models work, is that they're used to working on methods that are robust and work in the real world. And that kind of data-centric approach where you're really zooming into the details to understand what's going wrong is really important at scale training. And then with this kind of real world interpretability is like, we can understand RLHF methods better by kind of seeing them through robotics. I think everyone that does like a grad degree or some sort of real world learning has that moment the first time they see a robot learn in the real world. And I think that's extremely compelling and kind of drives a different type of inquiry, which is really important to kind of understanding how the methods work or may not work, because in the simulated domain or with language, there's just so much more flexibility to kind of fudge things and make it seem like it's working with different kind of levers that are being pulled, but kind of the direct reality of the real world is something that language models need right now. When evaluation is kind of broken for language, we need this kind of direct understanding of the methods. And then kind of the most floating point is like the long-term data engine. It seems very likely that eventually the data sets curated for robotics will converge with language in some way, to kind of add a sort of grounding in reality to the language models that right now are only really based on this internet data that everyone knows has issues. And I think that these qualities of real world grounding will be applied to language models. And the converse is also true, which is decision-making models will benefit from the ideas that language has basic reasoning capabilities. And we've already seen that. We're in the early days of that, and that's going to continue to grow, which is really exciting and can kind of bring these different communities together. So thanks for listening. I'm happy to take questions here if the technology works out, or you can email me, which you see in the bottom, and should be pretty easy to find. So thanks a lot for having me.
Thank you very much. So we have time for one question while we set up the chairs for the panelists. So also the panelists, please come forward.
Thank you. Thank you for this one. So in language, kind of the point of our chat is to align the model with what users want and what users need, because those settings really hard to actually define the reward function. Like, you know, how do you analytically, like, is this output satisfactory to the user? That's why I need. Instead of robotics, it's actually so much straightforward what the reward function is for a lot of these tasks. So, you know, given the data saw from Faye, you know, large transformers, LMs, DLMs, and robotics, and sort of merging together, do you actually think we need human feedback for robotics? What is this human feedback to give us that, you know, something more straightforward like a DLM reward function or some sort of classification, success type of thing could give us that, you know, human feedback would be superior to that?
Did you catch that, Nathan?
I think so. I'll kind of repeat it, and I think it's a great question. And I think it's a great question of essentially asking, like, do we need human feedback for robotics. Is that right?
Yeah, more or less.
Okay, so I think like this should be the question I expect. I think a lot of the things are not clear, but in the last point where people are trying to like understand how to use language models for control, that could be the way that where human feedback is needed, because then human feedback can address the shortcomings of the language models, like you were saying. But in the kind of classical sense, like extending the Cristiano et al. Paper where they figured out how to get some human signal to work, maybe not. And like but then the question is, how far does it extend? So if you can use language, if you can improve the language models that you're using for decision making and in phase talk and stuff like this, like, are there other ways to use that signal? And I think there very well could be when using very large models, but I'm going in with an open mind because I don't have many like proofs of signal or proofs of value from that yet. It's just people generally are extremely impressed by the quality of human data. And that might just be like teleoperation data in robotics rather than human feedback or comparisons or something like that. I think it's mostly about higher data quality than anything else, and even in the language model space.
Well, thank Nathan one more time.
All right, thank you. Thanks everybody. One more time for our speaker.
Hi, I'm Miller Jones. I work in Global Learning for Global Innovation. I'm speaking half on this.
Hello everyone, my name is Jeanette Hook. I'm Assistant Professor for Robotics in Stanford.
Hi, I'm Craig. I'm a researcher at Global Mind and Robotics.
Okay, thanks. So maybe we can kick off. We've heard the term foundation model a lot thrown around in this talk this morning. But sometimes people like understand different things with this term. So they would like to ask everyone maybe to try to define in your own words, like what you think is a robotics foundation model, what might be some of the ingredients necessary for it.
Yeah, maybe I can get started. So, in my definition, a foundation model is a large enough model that is trained on like diverse large data sets. We also have been thinking about emergent capability or generalization. So it can basically access a strong generalization capability and sometimes emergent capability that is beyond what's in the task that we train. So that's my definition of foundation model, and especially for robotics, foundation model is such a model that can do robotics tasks or embodied reasoning tasks or like manipulation or navigation tasks.
Yeah, I can cite the definition from the paper that coined the term, which was basically it's a large model trained on massive amounts of data, for in whatever domain really, robotics, computer vision, NLP, and they are often trained using self-supervised method, and they can be applied zero shot to downstream tasks that it hasn't actually been trained on. And I think that's just another way to say what they just said as well.
Okay, so I just work in a small academic lab. So for me, A foundation model is something I can basically steal from all the big tech companies without having to have all those resources myself and still actually be relevant in the era of deep learning.
Yeah, I agree with all the past things. I guess to make it a little different, I would say, to make it a little different, I would say, it's kind of a model that you kind of, you know it when you see it, and you have that wow moment. So I think for ChatGPT and all these other models, right, even segment anything, all of us have this moment of, wow, this model is really impressive and can do generalization, emergent properties, all these kinds of things that we didn't expect it to do.
So I'm a big believer in the idea that to understand language, you have to look at how it's actually used by people. And that's why large language models work so well. So if you apply that same logic to something that produces the following answer. The way people tend to use the word foundation model seems to more or less mean a good model, a really great model, a model with a lot of positive features. But maybe to make this a little bit more objective, we could say, well, it's a model people actually want to use. And it's a great model, maybe people want to use it. I think this also sheds some light on what this term should mean in the context of robotics. I think the fact that there is no such thing as a robotics foundation model, because so far there isn't a robotics model that lots of people want to use. I think we're pretty close to getting there, and maybe we'll figure out how to do that very soon.
All right, great. So moving on to the next question, something I personally struggle with is identifying not just what LLMs cannot do right now, but what they cannot do, what they will not do in the next year or so, or maybe longer. So what are some things that you don't think that you will just get for free when you download the next model? And that could be fundamental problems to try solving that would stand the test of time. We can talk about that second.
Yeah, so for me, I think it's the real like fine-grained manipulation or whatever you would never write in a textbook, like basically some know-how. For example, I am a cyclist and I sometimes need to adjust the radio, so can a vision language model look at it and tell me how to do it? I don't think we'll get there like anytime soon.
Yeah, I think in principle, if you can sample enough data for any problem, then you could train a foundation model, right? But so therefore, the question is, well, what problems can you not feasibly collect this data? That's maybe how I would think about it. And so I actually agree with Faye on the low-level sensing and motor control, as far as I understand. So I think I just find it, I just don't right now understand how we will be able to get the kind of data that a language model is currently trained on, which is like trillions, like multiple trillions of data points or tokens. How do we get that in robotics? The biggest data set right now is a million trajectories from the RTX effort, right? Like the OpenX embodiment conversion is in that. But even that is not necessarily maybe the kind of diverse data yet that we're looking for. So yeah, I'm not sure how we're going to get there. And so that's something that for me is a question. Like, what's the problem that we don't get the data for?
So I think sometimes to imagine where LLMs will be in the future, if you think about what LLMs actually being able to do that's superhuman or the same ability as human experts in certain fields. So I think we can expect LLMs to get to that point where they are as good as the best roboticists in the world. But even the best roboticists won't know how to solve some tasks, and that's sort of solve those tasks using a manually engineered solution, and that's where we need, let's say, vision motor control, and we're training robots with images and learning features that map images to actions. So I think it's, as Faye says, those fine-grained manipulation type tasks where we don't have sufficient representation to just feed into the language model. In the same way that even the best processors in the world wouldn't be able to design a hand-engineered controller for that, and they would need to go out and actually collect data and do some machine learning on that data.
Yeah, I guess this is a tricky question of predicting what emerging things will come. So with data, I think My guess would be long horizon planning is not going to emerge. Like, I think these models are not really capable of creating these long horizon kind of plans that will actually work in the real physical world. I think maybe another interesting one is kind of creativity or out of the box thinking. Like, I think, for example, whenever Einstein came up with at the time, given all the knowledge that he had, I don't think he just synthesized all the world knowledge or the expertise at the time and then just, did some interpolation or whatever in between. He came up with something completely different or a different way of thinking about things. And I think LLM's doing that in the near future.
The longer answer. So the short uncontroversial answer is in regard to language models in particular. We actually happen to know quite a lot about the theory of languages in efficient communication medium. We know that if I want to communicate something to you, then what I do is transmit those bits that you don't know that I know. But we know that the trouble that robots have is with things that old people know, moving their body, basic perception, things like that. Now, I said this was an uncontroversial answer. I think this answer is also partly wrong because nobody actually requires language models to be about language. And I think increasingly in the future, we'll actually increasingly see multimodal models. We're already seeing them right now. And as these get better, as the technical challenges associated with those are addressed, I think this issue will gradually go away. However, that brings me to the second issue, which is that models that are trained for prediction, and let's call them general prediction models if they're not just about language, are not doing rational decision-making. Rational decision-making also has a very specific definition. Rational decision-making maximizes utilities. Predictive models do not maximize utilities. We can torture them so that they make predictions that look like solutions to particular problems we pose, and that's what things like instruction fine-tuning do, but it still doesn't make them rational. So what we will really need in the long run is ways to use language models and other predictive models as what they are, which is predictive models, in the context of a planning or reinforcement learning group, which will actually turn them into rational decision makers. And again, we're seeing the initial signs of that kind of work happening already, but I think that in the long run, this will largely subsume the kind of tortuous prompting, instruction tuning, all that stuff that we do, and it will make them actually a lot more useful. But that's kind of the missing link.
Great. So we'll kind of use this to go into one of the audience suggested questions. By the way, there's a QR code on the right if you want to ask any questions, and you can also come to the mic towards the end. So we had a slightly spicy question, which is, what are the inductive biases that are original to robotics, or does robotics have any original ideas these days? When will we stop stealing ideas from the vision and language communities and just wrap them as new papers? So maybe we can go the other way again.
Well, I don't think it's stealing. I think it's, if you're working on AI, who cares if someone who came up with the idea considers themselves a computer vision researcher, machine learning researcher, or something else. The entire field of computer vision these days uses ideas that were developed for neural networks, which considered machine learning research at one point, but then the machine learning people wanted nothing to do with them for all the early 2000s. So I think, ideas are ideas. We should use the best ideas. And I think if increasingly the best ideas in robotics look like the best ideas elsewhere, I think that's tremendously exciting, and we should just embrace that.
Yeah, I agree. I mean, I think it's not clear why you would distinguish where ideas came from. I think one thing is these days there's a lot of low-hanging fruit. Like obviously this thing, only came out a year ago in full form anyway. And, people aren't gonna. Eventually, it'll plateau, and we'll realize which problems they do or do not solve. And I don't imagine that they'll solve everything. So I assume at that point we'll have to come up with new solutions.
So when I speak to somebody about their research and they say to me, "Oh, I trained this robot with end-to-end robot learning," and I say to them, "Well, what does that really mean?" They'll actually say, "Okay, well, I have a neural network, and then at the beginning of that, or particularly at the end of that, there's some other low-level controller that's mapping predictions of the neural network to some action." And I think that's one of the big differences between robotics and other areas of AI, in that actually there's a lot of things that we can model and analyze analytically to create stable controllers. And so I think that there's a lot of research in that aspect of robotics that isn't necessarily so relevant in other areas of AI, where we don't have a physical model of the world, therefore we can't apply classical mechanics to that world. But I think the really big breakthroughs will be coming from, and have come from, combining those classical analytical methods with learned behaviors, rather than just trying to learn everything from scratch. And there's a lot of work on trying to learn everything from scratch, and it is very interesting, but it might not, it might not be the best use of time. And actually, the best use of time might be to figure out what we can't do with classical controllers, and try to fill that gap with some learned behaviors.
Thank you. My guess is that this question comes from Jitendra Manik, but I'm not sure. I agree with you on the end-to-end thing. It's always a good question to ask, what are your ends, actually? And so I do think that controllers that have a long, rich history are really useful and still used. But I also want to highlight just hardware, because actually people in robotics, they are so creative, and they come up with so many great hardware solutions. Like, look at the cool new haptic sensors that came out within the last maybe decade or so. This vision-based haptic sensors, right? They're not used as much in robot learning, or certainly less, just because of the availability of this hardware. But I think that's going to make a huge difference if it actually becomes robust. The other things are cool new hand designs, right? These crazy hands with active surfaces that are completely departing from the anthropomorphic paradigms that most robots, or maybe the majority of roboticists have followed recently. And, think of the suction cup, so successful, right? Like, this is all hardware that comes from robotics, just as another data point here.
I would like to talk about a serious point and a non-serious point. So the serious point is that I think I agree with Jeanette that we contribute hardware, but also we contribute some of the research we contribute some of the research, like robotics in its broad sense is embodied AI. So it's about being active and like actively make changes in your environment. So for example, some concepts like affordances is also very helpful in other domains beyond just robotics. Secondly, robotics is dealing with a lot of reasoning and planning, so that's also very helpful for the general AI field, or like making more sophisticated large language models. So essentially, learning how to build an agent in the physical world can teach us a lot about how to build an agent in the virtual world, or how we advance AI in general. Second, the non-serious point is that I think roboticists are very optimistic, because robotics doesn't work yet, and we're like working on this for a very long time. So this can probably bring some optimism for the AI field.
Thanks. Another question that was asked by the audience was on the basically on the role of industry and academia, like due to the bigger model size.
kind of have different responsibilities in this type of development. And of course, there are also like collaborations and shared works. I think OpenX environment is one of the first steps to facilitate this type of collaboration.
Yeah, thanks. Yeah, I think I'm really excited about collaborations like the OpenX environment consortium and collaboration, I think it was called. I think I really like that was spearheaded, for example, by Google. So that's great as an initiative. And then maybe as another answer to this, I want to channel Professor Fei-Fei Li, who told me at some point, you were by the right? Yeah. Who told me at some point, well, you should always think about something that is 10 years out and that industry is not going to do within the next year. And yeah, just to remind everyone, right, like the big ideas, or many of the big ideas that maybe the current explosion in AI is based on also came originally from academia and maybe have, leveled off or fallen out of favor for a while and then came back because there were new insights that made them actually useful. And yeah, that's maybe something good to remember as well. I also want to channel an unknown anthropologist, and Indiana Jones from NYU professor there, his name I've forgotten, and he just said, study everything, because you don't know what's going to be important at some point.
So I work in academia. I don't really have big collaborations with industry. But one of the nice things about that is it does force you to try to be a little bit more, let's say, data efficient than what is possible in industry, where you've got access to lots and lots of data, lots of engineers, lots of compute. So, for example, with imitation learning, a lot of the work we do in my lab, we're trying to develop very, very efficient imitation learning methods, which might not be so important in industry, where actually you can just get 100 demonstrations per task, and it's relatively straightforward to get that. But in academia, it forces you to be think things a little bit more differently and try to be more efficient with that data, which ultimately then might move on into industry as industry adopts those techniques.
Yeah, I guess similar to what a lot of people have said. I mean, I see research as like a genetic algorithm for exploration, and you ultimately don't know which ideas will pan out. I like the fusion models because, it's some kind of very math-heavy 2015 paper, and obviously has led to really great results. So, ultimately, I think the thing you should do is, there are different flavors of research you can do. I collaborate a lot with industry, but I also have other non-collaborative projects that are more fundamental, like Janet said, like look out at what are the 10-year kind of problems that industry is not tackling. Often they are, by definition, a little bit more kind of short-term driven, so looking at those kinds of things. And I think one thing that we should maybe consider the community is how to kind of ensure the right incentives. So I think, for example, in reviewing, I think these days it's getting a little bit more industry like short-sighted, where we want, results for everything that's state of the art and things like that. And I think maybe providing structures to broaden that to support more basic research, again, that may not lead to anything, but may also lead to the next breakthrough.
I think the other panelists provided a lot of really interesting and creative answers to this, so I'm going to just add a little dip on top of that rather than trying to answer the entire question. Otherwise, I'd just be repeating what everyone else already said. I think maybe one thing to consider is that there is, it's not really as much about academic research versus industry research. You could think about it as fundamental research and applied research, but it's very tempting to overload those words and sort of romanticize them. But here's the thing, especially if you're working on modern machine learning, if you're trying to make something really big, you're probably not making fundamental changes to the basic design. And if you're making fundamental changes to basic design, you're probably not making something big. So there's going to be a trade-off. And it doesn't matter whether you have in your basement working by yourself or you're working with a team of 100 engineers and 10,000 GPUs, that trade-off is still there. You can't both make it big and make fundamental changes. So I think that the right way to approach that is to think really carefully about what your vision is for the kinds of methods that will actually be effective at solving your problems 5, 10 years down the line. And perhaps those are the methods that we have now, in which case you just have to make them big, or perhaps they're something very different, in which case you have to make fundamental changes. Figure that out, and then figure out the appropriate plan to pursue that vision.
Great. I like a few things that Solt and Jeanette pointed out. So maybe the next question here would be, as area chairs, senior area chairs, and for us as reviewers, what should be the right metrics to evaluate papers on? Because there are a lot of ideas which I don't see as, oh, this is the next big thing, but we should give them a chance. How do we evaluate and review papers as a community?
Very carefully. Well, I don't think there's a it was golden numbers. And the numbers better be like, at least this much bigger than the other numbers, and then it's all good. Or, it has a theorem, and has a bound, and the bound has a number, and the number has the next one, and the next one should be lower than the previous one, something like that. So I think the most important thing is just get the templates out of our mind and really pay attention to what are the claims and are they evaluated. But I don't think there's anything magical about it. Like, it's a formula that I think we all really understand. We just have to do it.
And I don't know if Sergey did this on purpose, but it's pretty much similar to the TMLR, Transactions on Machine Learning Research, which is exactly that. Make some claims, and of course it just has to be significant claims that people will care about. And then did you provide evidence for that claim? So ultimately, I don't want to template that. What kind of contributions you make? I think ultimately it can be empirical contributions, that's fine. If you show that, you beat something by 10% by scaling it up, that's cool. I think people should know about that. On the other hand, if your contributions is not on the empirical side, then you should make some theoretical or other contributions. So the paper should just have a contribution that adds to the scientific body of knowledge. And again, it can be empirical or theoretical. So I like that.
finding the problem because there are so many out there in the first place. And I think we should use that because that's what I like about reading robotics paper. I much more often learn something new compared to read the average. Not even sure. The windows now in the comments.
Okay, so we have had some nice questions so far. So we are moving on to the next phase of the panel. And basically we will ask each of you to give a statement that you think the rest of the panel will disagree with you on.
Or something that you massively disagree with one person. You pick a fight. Maybe end in the middle because he always gets lucky. You start first.
Well, I'm just going to say something that at least somebody here will probably disagree with, but what is that? Okay, let me think. Well, it's also, okay, maybe, so the work that I do is all on manipulation. Let me say this. Locomotion and navigation are solved, and the only thing left is to solve is manipulation. I'll pretend that's my opinion. It is somewhat, but it's not quite as direct as that.
Defenses are allowed.
I win.
I think simulation is a nice tool, but it's not going to get us all the way.
I think you have to go with soul next. That was the soul topic.
You went there. But, I mean, let's see. I think simulation. No, it's fun. I don't feel targeted. I am not wedded to any one thing. So, I think simulation is basically one route to scale, which again, if we believe scale is something that has made other fields successful, I think in the real world, world is just awful in terms of running actual and gathering actual experiments. And I think, again, I mentioned this during my talk, there's a kind of a big chicken and egg problem where I don't think we can, Tesla solves this because they have cars and they actually drive, not by themselves, but they drive, the humans drive them, and it gathers a bunch of data. On the robotics side, it's not, home robotics, for example, it's not clear how to do that. So I think I'll defend simulation in that regard. It really can bootstrap this chicken and egg problem where we can just scale up to as much as our compute can handle. super made by increasing tons of money, or engineering effort which costs money. But ultimately, it's not clear to me what is the path to having like a home robot that will actually, I don't have to pay hundreds of thousands of dollars will actually do the tasks that I want, which is typically dishwashing, cleaning the house, and so on. And that will work reliably such that I don't need to call like an engineer every day to fix that robot. I don't know if that's controversial.
I guess maybe for something that's along the theme of foundation models, I think that maybe the different problems in robotics are maybe much more similar to each other than perhaps we might appreciate. And I think this is maybe like a little bit of a blindness that we might have also as domain experts. Like if you work on robotic manipulation, you know a lot about manipulation, and it looks like there's a lot of manipulation things going on. And if you work on navigation, there's a lot of navigation things going on. I think we'll actually increasingly see over the next few years that very similar sets of tools, or maybe even exactly the same sets of tools, maybe even the same actual models, like literally the same model weights, end up solving broader and broader cross sections of robotics problems. And I think that's going to be really interesting because perhaps right now we could look at the different fields and say like, well, autonomous driving is a little different, right? Because autonomous driving, they have these safety concerns, but they also have tons of data. And then like maybe the manipulation is a little different because maybe it's okay if the robot is a little bit less safe, maybe, but there's a lot less data. But I think the more and more that the methods and even the models themselves are unified, the more these areas are kind of united in their strengths, in the sense that, well, if you have lots and lots of data in one domain, but those domains are really very similar, well, that's benefiting everybody else. If you figure out how to do robustness in one area, that's going to benefit all the others. So I think these problems are actually, at some level, very similar, and maybe that shouldn't be that surprising, because if we look at the theoretical foundations of learning-based decision-making, they do treat all robots equally in the sense that, well, there's actions, there's controls, there's states, observations, etc., and it doesn't matter whether it's driving on wheels or washing dishes. But I think we'll see that what was once kind of a theoretical conceptual idea really come to fruition over the next few years as our data sets get bigger and our models get more powerful and our algorithms get better.
Yeah, maybe an optimistic take, which is I think over the next couple of years, like robotics or embodied AI will be the central place of AI development, because like for large language models will soon run out of tokens, and like we'll focus more on like this active type of learning, active data gathering, and we'll see bidirectional loop from foundation model research and robotics research, and doing robotics help you build a better foundation model.
Great, so with those takes, everyone offended by the takes, we're opening it up for questions. We have some online questions, but maybe people in the room first.
Come to the front.
Yeah, just come to the front and the mic is passed. Questions for them?
So kind of building on that last point when you're talking about and collecting more data and helping respondents learn in the places where they're uncertain. I wonder your guys' perspective on like the best way to do that, and like how can maybe this model communicate like what it doesn't know and what needs to be gathered for it to learn how to do the task at hand. It's not always obvious when you're deploying these models or training them. Who's this looking for? I mean, I guess anyone, but I guess Faye and maybe Sergey.
I'll say something that's kind of a lot of these questions about being smart with collecting data somehow become a lot less prominent once the thing is real. So maybe the single best thing that we can do to bring Faye's vision to fruition is actually have somebody, some enterprising company, actually build a system that people actually use, so that there isn't like 100 robots, but there's like 1 million robots, and then suddenly the problem just kind of goes away, because, well, if they're out there in the world doing the thing people want them to do, then almost definitionally they're collecting the right data because they're doing the thing that people want.
Yeah, I guess what you ask is essentially a code start problem. Like basically, you don't have.
And I think even the Tesla example, I guess Cruise was taught that they have people actually driving the cars for, because, you know, they intervene every 3 minutes or something. So maybe one solution could also be putting lots of robots in homes that maybe are like jointly like controlled by humans, but also maybe robots. But I agree, like in terms of, yeah, the selection problem should be solved by somehow getting lots of robots in actual homes at a large scale. And then you'll be able to really solve a lot of these problems if you can scale.
I think another thing to think about is if a human, let's say, take reinforcement learning, if a human is going to be there to provide rewards and reset the environment and give feedback to the robot, why not just spend that time providing demonstrations if we're trying to optimize for the amount of data we can collect, good data within a specific amount of time with a given amount of money. So yeah, I feel like invitation learning seems to have taken off a lot in the last few years because of that very reason.
Hi, I have a question. So if the embodied agent is going to help building foundation models in like next few years, like what actual information does embodied interactions can bring to foundation models that is not able to get from vision or language data?
Yeah, I can answer this. So I think in vision and language, there is fundamentally a lack of actions and information in the data about what the effect is of your action when you execute it in the real world. And so that's what an embodied model should bring us, right? Like some understanding, like I'm in this state, I'm doing this action, what do I expect next? Or even an inverse reward, reward learning, for example, inverse reinforcement learning, and things like that. All of this depends on knowing the effect of the action, or somehow having the action as part of. It's the difference we need to computer vision and a natural language model to a robotic model.
Yeah, I want to briefly add one more point. So let's say if we can find another different point from the embodied AI domain and like the vision language modeling domain. So all the large language models are using next token prediction. Essentially, they're auto-regressive decoding. So it's really just predicting the next token, and it does not necessarily have the deliberate type of thinking or planning or reasoning. However, in robotics, like people have extensively used optimization to derive something. That's maybe another part. Like, can we give foundation models more reasoning and planning capability?
I can give a kind of maybe a slightly weird answer to that question. I think that while there's a lot that we could say about the quality of embodied data over, let's say, passive data from the web, I think in the long run, and maybe this is the overly long run, the real answer will be weird enough quantity. Why? Well, all of the data that you can mine from the web was at some point created by humans. In fact, if it wasn't created by humans, then you probably don't want it because it was probably created by a language model. So now let's think about that for a minute. What that means is millions, maybe billions of people were laboring to create all of this stuff that they put on the web, and we're using that to train our AI systems. Well, if the point of building robots is to automate things that humans would otherwise have to do themselves, perhaps ultimately what they'll really automate is the generation of all that content. And certainly, coming back to the autonomous driving example, it makes it kind of obvious. Like, if every car is a partially autonomous car, then the data collected autonomously by cars has to be larger than the data collected by humans, because if the human is driving the car, well, the car is still that same partially autonomous car, right? In the same way that if you have robots that are actually doing a job, like they're actually washing the dishes, Well, if they're doing that well, there's going to be far more dishwashing data from those robots than humans ever recorded themselves in all of history since the internet was created. So I think in the long run, actually, the big power of embodied data, weirdly enough, will be that it will be much, much larger, and it will keep getting bigger on its own with minimal human effort.
Yeah, one thing, I mean, I talk about interaction, not like with the world necessarily, but other humans, or humans or other like models. I think personalization, it's not really specific to robotics, but I think ultimately if you have robots in the home and they're like in your personal space and they're expected to perform autonomous tasks, they will have to interact with you and the environment to understand what you want them to do, right? So slight kind of differences in the rewards or the objectives. And again, this is, I think, also true for like chatbots, but I think chatbots, I don't know, in some sense, like language questions, like the generic answers that you get averaged across all humans is somewhat like similar. Although, you know, again, ChatGPT, I think, just is going to release like a personalized version where you can, you know, name it and give it its own like system prompt and things like that. Similarly, when it's in the physical world, you want it to do particular tasks in particular ways because you know, are OCD like me and you want that cup exactly there, not crooked or whatever. Other people might have other kind of constraints. So I think personalization is a big reason why robots will ultimately want to gather experience in the environment.
We have one more question over here from the audience.
Thank you very much. So we've heard of this vision, I think it's been a vision for a while, to pre-train something that works, put it out there in the world, generates more data, orders of magnitude more data, we fine-tune, it gets better, we put it out there, we fine-tune it, gets better until it works perfectly. So, but it seems to me, by definition, once we put something out there in the world, the data it generates must be suboptimal, because if it's optimal, then it already solves everything. You know, there's nothing to learn. So by definition, those data sets that we get back will be suboptimal. My question is, how do you foresee learning from those data sets? Because it seems to be able to do that. We still need to scale our current sort of reinforced learning approaches or whatever by 2 to 3 orders of magnitude. And it seems to be in the offline case, or even off-policy case, when we need to train it at 100 billion scale or like 50 billion scale, it's still very difficult. So I'd like to hear the panelists' thoughts on how do we use this suboptimal data in this new, very, very large model regime.
So I think you laid out a good research agenda. Like, I think we should do that. I think we should figure out how to get rational decision-making algorithms, reinforcement learning algorithms, to scale up to 2 to 3 orders of magnitude larger data sets and models. I think you're right that it's challenging, but I think, you know, that's a very well-contained, very well-defined research problem, and I think that we as a field will make progress on it. I think to get a sense for the progress, you can also just go back a year, 2 years, and see how far we've come since it started, right? Like, you know, 3, 4 years ago, I think most of the machine learning community didn't realize that offline RL is a different problem statement than off-policy RL. Now that's, you know, at least in my course, that's like a textbook kind of fact. In terms of the size of the models that we can train and the kinds of robotic systems they can control, it's increasing all the time. So I think you're right that it's a challenging problem, but I think that that's a great problem to work on.
I have a potentially controversial thing I want to throw out that I came up with while we were talking. I don't know, maybe it's not controversial, but I'm thinking if we had better hardware and all these cool sensors and better hands with better wrists, just generally better hardware, a lot of the algorithms that we're developing right now that deal with RGB data purely as input will be obsolete and not be useful. You know, given that we maybe have hardware where the data produced is actually much better and the robot is much more capable in the first place. What do people think? I'm assuming that these cool, you know, robotics devices, sensors and so on, and actuators, they're robust, right? So in the sense that they are at the level where we can potentially collect a lot of data.
I think that's probably true. But I guess, are you saying, I'm imagining the algorithms themselves might be the same. It's just the data, you need much less data because the hardware is much better. And so hopefully the algorithms we're developing now are still relevant in 5 years' time. It's just so much, they're going to train much more quickly on the better hardware.
Yeah, that could be one outcome. That is just you need less data. The other one is that we're trying way too hard right now because the data is just not good, right? Like it has a lot of there's a lot of things that are not observed, but once you have actually sensory data coming from haptic sensors, from audio, from you know, the other day someone asked me if a robot can smell, you know, these kinds of things. If a robot had much more ability to observe the world, then maybe all these algorithms are actually way too complicated. Just a hypothesis.
All right, that's it for our first panel. Thank you a lot. Let's thank our panelists. We will turn off for the lunch break, but before you go, if you could please fill out the survey that CoRL asked us, so they know that you are attending this workshop and they let us organize maybe next year a third edition. Yeah, so we will continue at 1:30 after lunch with Ed Jones' talk. So thank you everybody and see you after lunch.
Welcome back, because every my manipulation has no problem with this.
Just forgetting. Thanks a lot. Yeah. Oh yeah, thank you so much. Yeah, appreciate adding a little bit of it. Yeah. In-person conferences are great.
The recording has stopped.
They're kind of like, I think nobody I groups, they shut down the robotics thing after that. So hard to keep. You know, like, you know, everything to do for being mature. They like the opposite. He was also
Actually, I might be able to. I mean, we might be okay, actually. Ed, do you have the link?
Yeah, it's not allowed me to join for some reason.
Admit, Berkeley's trying to attack you.
You know, sometimes you get this thing where it's like, I mean,
Oh, I saw that too before.
normally it gives you an option to override it or something.
Yeah, yeah.
To override.
I switched to like another Google profile and it let me.
I just tried in incognito. It didn't.
Yeah.
Let me see if I can just join by like actually putting the. Do you have like the? Is there like a number, meeting ID or anything?
Would you like to try this stream? 964.
Okay, yeah, let's try this. 964
562
62
520
20
3.
Okay. At least it's...
You were able to join?
Okay, and then yeah, let me know when you want me to.
Amazing. Okay. That looks great.
Great. Okay.
I think this is. Do you have speaker notes?
No.
We could go so that you like just don't do the presenter view, but just mirror view.
That's fine. Yeah, I don't have any notes, so I can
Okay,
just.
yeah, sure.
Does that make a difference? Like,
because Zoom will show this.
Zoom
shows
Zoom.
your screen.
All right. Okay.
And sees that screen.
So
we just want to mirror these two, I guess.
Yeah. So that's done. Like in here, isn't it? Just.
Well, what did you just press?
I just pressed play from start. I think if you go here. Browser kiosk, it might be that one. Yes.
Great.
Is that it?
Yeah, that looks great. Okay. I think you're able to advance.
No.
Okay, we can go back to the older role.
That's weird. Let's try one more time. They got timers or something.
Presented by an individual window. Now you okay.
Okay.
This looks.
I think the kiosk thing is like
if you're like
just timings or something. I didn't know.
Yeah. Okay.
All right. Great.
Okay. Let's see. Well, it's 11 past. I think there's maybe 10 viewers across Zoom and right now. One more minute to start.
Okay. Yeah. Whatever you want.
I enjoy watching them. I mean, I've been pressing that these are not No, we had this whole I told you eventually. I'll just get it. It's like because like I already ready for one. Very good. And I think she sort of so how do you decide what's going on? And so it's just like right now like I don't know crazy about like I sort of like with these then I mean, they're not going to serve. Yeah. That is right. First time I got it's not the month right. There you go.
Hey, thanks for bearing with the lunch delays. We'll about to get started in about a minute or so with our first speaker, Hey John. That one? You okay? You can get settled, like start clipping in, and when you're clipped in, you can just flip that switch. Okay. All right, then let's go ahead and resume LangRob workshop. So I have the pleasure today of introducing our next speaker, Dr. Ed Johns. He's the director of the Robot Learning Lab at Imperial College London and a senior lecturer associated with his work lies at the intersection of robotics, computer vision, and machine learning, and he and his team are currently studying visually guided robot manipulation. He received a BA and MN in electrical information engineering from Cambridge University and a PhD in visual recognition from ICL. Following his PhD, he was at UCL before turning to Imperial College as a founding member of the Dyson Robotics Lab with Professor Andrew Davidson, where he led the robot manipulation research. In 2017, he was awarded the prestigious Royal Academy of Engineering Research Fellowship for his project Powering Next Generation Robots with Active Simulation, Deep Learning via Simulation. Then in 2018, he was appointed as a lecturer and founded the Robot Learning Lab. He established College's first course of robot learning, which he currently teaches at the graduate level. And personally, I've really enjoyed it. It's very visceral demos and talks over the last years, and I'll let you take away.
Thanks a lot, Ted. Okay, how's lunch? Good. All right, so I'm going to talk about, the title of my talk is, do we really need action data, or are image and language data enough? So the work in my lab is really based on robot manipulation. So let me just move this. So here's some examples of tasks and controllers that we've developed and learned in our lab. We're focusing on manipulation. I think this is a really, really hard area of robotics. There's a long way to go. There's lots and lots of research left to do. Now, some of these methods developed here required action data, and some of these methods didn't require action data. And by action data, I mean, let's say, human demonstrations of tasks. So you can try and have a guess, if you like, to decide which of these you think required action data and which of these only required image data and language data. And I'm going to reveal through this talk which is which. So let's look at the title of this workshop. The title of the workshop is LangRob, Workshop on Language and Robot Learning. Now, of course, there's much more to robotics than just language. Okay, if you say to ChatGPT, please make me a cup of tea, this is what it responded with when I put this in recently. It says, I'm unable to physically interact with the environment to make you a cup of tea, but I can guide you through the process. Here's a simple way to make a cup of tea. So it's trying to help me out as much as possible. It knows it can't physically interact with the world, but it's got some intelligence there. However, in reality, we need to add on a few things here. First of all, we need to give it some way of interacting with the world. We need to give this a robot arm, some actuators so it can physically interact with the world. We also need to let the robot or the controller know where things are in the world, and it can do this via an image observation. And then the thing in the middle would become something like a control policy. So this is a little bit more typical as to what it looks like when you're training a robot. You'll have an image observation at the input, maybe a language command, which dictates what the robot should do, or commands the robot. Then you have some policy, and then the robot will execute an action. So this talk's going to be all about images, language, and action, the three components to robot learning. Now, the problem that we face in this space is that there's lots and lots of image and language data out there. And this has really led to lots of the breakthroughs in other areas of AI. Loads and loads of language data, loads and loads of image data, hardly any action data. So the amount of action data that we currently have is very, very small relative to the amount of image and language data. And it's one of the real challenges in robot learning. How can we actually get that critical mass of data that led to breakthroughs in other areas of AI, such as language models and computer vision? And in this talk, I'm going to basically discuss three solutions to this problem. Three solutions to how can we get, either how can we get that action data, or how can we deal with the fact that maybe we can get around this and actually not need action data at all. So the first solution is just to more efficiently collect image, language, and action data. Okay, so let's say, okay, we're going to resort to the fact that we need to collect action data. We need to provide some actions to the robot learning algorithm. How can we do this much more efficiently? And I'm going to just briefly explain two methods that we've been developing recently. These are two methods that we have papers here at CoRL, and we'll be presenting these tomorrow. And these are two very efficient imitation learning methods, but coming from very different perspectives. Okay, so one of these is what we call a pose estimation perspective on imitation learning. Okay, and it's a very simple idea, but it works very, very well. And we're able to learn lots and lots of quite complex tasks from just a single demonstration using this idea. And it's based on this idea of trajectory transfer. So let's say we have a demonstration scene here on the left, and this is a demonstration. Now this object is going to move over to the other part of the table, and we've got to transfer that trajectory to where that object has moved. The problem is we want to do this without having any prior knowledge of these objects. We don't want to have to assume CAD models of the objects, because we just want to throw a robot into a room, provide some demonstrations, and then allow the robot to then perform those tasks. So how can we do this without assuming prior object knowledge? Well, what we can do is we can deploy unseen object pose estimation, okay? So this is where we have a single image, a single kind of reference image, and then a live image during deployment. And we've got to estimate the relative pose of those two objects, the objects in those images. And through this, we can mathematically formulate the problem such that we can transfer that trajectory from the demonstration scene to the deployment scene. And it works very well. So here's some videos of my students, Camille and Pietro, showing a single demonstration to the robot of these tasks. Then immediately afterwards, the robot has learned that task and is able to then perform this task even though the object is moving around the environment. And we could also just put some distractor objects in front of the robot, and the robot's able to learn this task. And this is very, very efficient, right? So we're performing a single demonstration. That's all we need to do. We can step back, the robot will immediately learn that task. And these are tasks requiring quite a lot of precision, maybe 2 or 3 millimeters of precision here. And this is much more efficient than, let's say, traditional behavioral cloning methods where you're simply providing hundreds and hundreds of demonstrations. So we've got a very nice, efficient way to teach robots here. And this addresses one of those limitations I was talking about, where it's actually very difficult to collect data. So maybe we can collect that data much more efficiently, and that's one part of the solution. What about generalization? So let's say we want to teach a robot how to interact with some objects, and then we want to show it different objects of the same class. Here, my student Vitalis is showing some demonstrations of how to pour from a teapot into a mug. And then immediately after those demonstrations, the robot has then generalized to novel objects. And the way that we're doing this is we're doing this with in-context learning. We're conditioning a graph neural network on a set of demonstrations and a candidate alignment of the test objects, and we're predicting the energy of that alignment. And we're training this energy-based model such that during inference, we can minimize the energy, and then hopefully that will give us the optimal alignment. And the thing that I really like about this project is actually we train this over randomly warped objects in simulation. And the reason this is nice is because then when we deploy this, we don't have to assume any prior object knowledge. So we don't have to assume the class of objects that the robot is interacting with, which is often what other methods in this space require. So we can simply put these, provide these demonstrations to the robot, and then the robot is able to learn these tasks by generalizing from the demonstration data to the deployment data. And you can see here, this happens immediately after those demonstrations. So there is no period of training as such. It's all done using this in-context learning with that big graph neural network that we trained in simulation. So that's one part of the problem. This workshop isn't really on imitation learning, but I just wanted to put it out there that one solution is just to come up with much more efficient methods of collecting that action data, okay? What I'm really going to be talking about in the rest of the talk is how we can avoid collecting action data at all and do as much of our robot learning with just image data and language data, because that's what we have lots and lots of in the world, okay? We've got lots and lots of image data, lots and lots of language data. Can we exploit that and then get robots to perform manipulation tasks without actually having to provide any demonstrations or doing any reinforcement learning or anything like that. So here's another solution. We're going to exploit the image and language data, and we're going to generate some language conditioned goal images. And the reason why this is potentially a good solution is because once you've generated your goal image for that task, often you can actually model a controller such that a robot can rearrange objects in order to recreate that goal image. And that's because for a lot of tasks like pick and place tasks, we do have very good understanding of the dynamics there. We know how to grasp objects. We know how to move an arm from point A to point B. We know how to release an object. So all of that right-hand side of this controller can just be manually engineered, and we don't actually need to collect any data for that. All we've got to do is collect the data that maps the image observation and the language command to this goal image. But of course, that comes from OpenAI or whoever wants to build this network for us. So I'm going to take you through a couple of methods here that we've developed where mapping the original image observation and a language command to an intermediate goal image allows us to perform some language conditioned tasks. The first method that we looked at when we started studying this was inspired by OpenAI's DALL-E 2 when it came out last summer. And we started seeing these amazing images that we're able to generate just by putting in language descriptions of the images we wanted to create. And we started thinking about, well, maybe there's something we can do with this in robotics. Maybe we can use these image diffusion models as imagination engines for robots. And this led to our idea, which we call DALL-E-Bot. So in DALL-E-Bot, what we do is we take the initial scene and then we create a textual description of that scene. Then we use an image diffusion model to generate an image which describes, which shows the objects in a certain arrangement. And hopefully that arrangement will be a natural arrangement of those objects. So these objects aren't just going to be randomly scattered around. They're going to be an arrangement that has been seen lots and lots of times in images on the internet, because that's what these image diffusion models have been trained on. And then once we generated this image, we can recreate that, that scene in the real world by using pick and place planning. So I'm going to take you through the pipeline here quickly. We start off with an initial observation. And we detect all of the objects in that image observation. And we generate some masks for those objects and then some semantic features. And we use a language model to essentially create captions that describe the image. Once we have this, we generate a prompt, okay? And the prompt is a distilled quick description of the scene that will allow us to generate this image here. And as you can see here, in this case, what we're generating is an image with a natural arrangement of those objects. So we've got the knife on the right of the plate, the fork on the left of the plate, the spoon on the top of the plate. And this is all captured just using this web scale prior. Okay, we don't have to tell the robot that knives should be to the right of plates. It's just that all of the images that the robot or the diffusion model has seen happen to have knives to the right of plates, or at least that's the default mode. Once you've generated this image, we can then try to map the objects in that generated image back to the real world. And the way we do that is we use these semantic properties of the masked images, segmentation mask, to find an alignment between the real objects in the scene and the generated objects. And then finally, we can recreate that generated image. So all of this requires no action data, okay? The robot is able to create this image and then use a sort of a manually engineered controller in order to do the pick and place planning. What we have to deal with, though, is some of these images are generated with some strange appearances. So, of course, image diffusion models a year ago or over a year ago when we were doing this often would give us quite strange images, and we had to filter them out using a variety of techniques. Probably nowadays, these image diffusion models are much better and we wouldn't have to do this, but at the time, this was necessary. Here's an example of what this looks like. So we just place a plate, a knife, a fork, and a spoon in front of the robot. The robot then creates that textual description of the scene, generates the image that I'm showing in the top right here, and then it's recreating that image by moving the objects around. Now, none of this requires any action data. We didn't have to have any demonstrations. We didn't have to have any demonstrations of the fact that the knife needs to go to the right of the plate, nor did we have to have any demonstrations of how to move the knife given the target pose of that knife. So all of this is kind of action data free. We just sort of create this system that uses this web scale prior and is able to then use that engineered pick and place planning in order to maneuver the objects. Here's some more examples. So on the left, we have a robot creating an office scene, and it has an understanding that the keyboard should be well aligned with the monitor and the mouse should be to the side of the keyboard. On the right-hand side, the robot understands that fruit should go into baskets, okay? So when it sees an apple and 2 apples and an orange and a basket, it thinks, well, actually, probably the best place to put the apple and the apples and the orange is in the basket. Now, you might be thinking, well, that's quite a trivial task just to sort of put things in baskets. It is a trivial task, but there are lots and lots of trivial tasks out there, and we don't want to have to manually design controllers or manually design rules for where objects should go relative to each other. So this allows these rules to come through naturally through these image diffusion models. And that's really the power of DALI-Bot, is using this web scale prior to understand where objects should go relative to each other. Here's some examples of comparisons with some baselines. So on the left, we've got a random baseline where we're just putting objects randomly. Then we've got a geometric baseline where we line up objects in a row. And then an autoregression version and a version of DALI-Bot without this filtering that I mentioned. And we did some user studies and we presented the results to participants, and DALI-Bot won in terms of neatness and convenience, these metrics that we designed. So it's clear that these web scale priors have meaningful understanding of the geometric relationships between objects that we can use in robotics. Let's talk about the limitations of DALI-Bot. So one of the limitations is that generated images might differ to the real objects, okay? So we had to do this semantic alignment between the generated objects and the real objects. And that kind of works in some scenes, but it's not necessarily going to work in general. Second limitation is that we can only generate 2D images, okay? So these image diffusion models are trained on 2D images, therefore they're going to generate 2D images. The real world is 3D. A third limitation is that in the DALI-Bot implementation, the robot couldn't follow a specific command. Really what we were doing is we're saying, take these objects and arrange them in a way that you think is the robot is the most natural arrangement, but we weren't actually telling the robot where to place objects. And actually, we might want to have a little bit more control over what the robot's doing. So here are the 3 solutions that we came up with. First of all, instead of just generating an image using the image diffusion model, we're going to take those real objects and move them around in the robot's imagination and allow the robot to see what those objects would look like in different positions. But we're going to do that with the real objects rather than generating novel objects. And therefore, we don't have to have this problem where we might be generating strange objects that don't align with the real world. Second problem was that we can only generate 2 images. So we decided to actually start building up a 3D representation of the world. So we started building up 3D nerfs of the scene and then using that 3D space as the imagination space. And that's the space in which we're going to move around these objects and imagine them in different configurations. And the third issue was that, well, with DALI-Bot, we couldn't actually command the robot to perform arbitrary arrangement tasks. So now what we're going to do is we're actually going to imagine images, imagine objects in certain poses, render images, and then compute the clip similarity between those imagined object poses and the text command. This then allows us to take in a text command and find the pose of the objects which is best aligned with that text command. And this led to our method called Dream to Real. So on the left-hand side, we have an initial scene where we've got some shells and some bottles and some other distractor objects. And the human command here is move the strawberry milkshake bottle to make 3 milkshake bottles standing upright in a neat row. So what do we actually do in practice here? First of all, we're going to scan the scene. So we're going to move the robot around the scene with the camera and build up a 3D nerf of that environment. And that's what the turquoise image is showing here. The second stage is we're going to then take the object of interest, which is here the bottle, the strawberry bottle, and render it, put that bottle in lots of different poses, and then render images of those poses, and then compute the similarity between the images rendered of those objects in those poses and the text command. So for example, here on the right-hand side, you can see there's a high clip similarity between, for where the bottle is on the top shelf. There's a high similarity between that and the command 3 bottles in a row. Whereas when the bottle is imagined on the bottom shelf, there's a low similarity there. So we're moving this bottle around in the robot's imagination in 3D, and the robot is comparing the clip similarity between an image rendered in those poses and the text command that the human has given. And that then allows the robot to figure out where to place the object in the environment. So here's what that looks like in the real world. This is all zero shot, so we're not providing any action data. The robot is able to realize that it needs to place the straw bottle on the left here rather than, let's say, on the bottom or anywhere else in the environment to match that language command that we are providing. Here's some more examples. So let's say the text command is put the apple inside the blue and white bowl. What the robot's going to do, it's going to imagine that apple in lots of different poses. And when that apple rests on top of the blue and white bowl, there's going to be strong clip similarity between that image that's rendered and the text command, put the apple inside the blue and white bowl. So then the robot is able to realize, well, that's where the apple should go because that's the best pose according to this clip similarity. And here's a final example. So this is talking about geometric arrangements of objects here into shapes. So the command is move the black 8 ball so that there are balls in an X shape. And again, you can see in the heat map here on the top right, the best place for that ball to go is where it would complete that X shape. So we're able to allow robots to have this imagination in 3D space now, and then integrate image and language models to enable the robot to decide where to place those objects without us actually having to provide any demonstrations or without us having to provide any of this action data. Okay, and so we did some experiments here, and this is probably I don't know, the simplest experiment to understand in the time I have. The takeaway message here is if we just capture a single view, like a point cloud of the scene, and then render that point cloud, that doesn't work very well. And it's because that point cloud isn't really capturing the full shape of the object. Also, the point cloud, if you render a point cloud, that image doesn't look very realistic. And CLIP is trained on real images. So CLIP really needs highly realistic images to be rendered in order for it to be, for that CLIP similarity score to be meaningful. So we found here that if we're using our dream to real method and actually creating a NERF of the scene, allowing that NERF to render those objects, because NERFs create us very, very good photorealistic renderings, then that is necessary in order for CLIP to start working. And if we just do something more simple, like render a point cloud, it doesn't really work very well. Okay, so that was solution 2 to the problem of there being hardly any action data out there. We just create these goal images, and then we have a manually engineered controller which can go from the goal image to that final arrangement. But what about tasks where we're not just doing pick and place? Okay, so of course we can design hand-engineered controllers to do pick and place given a goal image, but there are a lot of tasks out there that actually are more complex than this, and they might need something else beyond just this manually engineered controller to solve them. So we started thinking about our third solution here, which is, can a language model actually just predict the trajectories themselves directly? Okay, so really what we're saying is we're going to replace the human's hand-engineered model here and see if a large language model can make those predictions without a human needing to be there. This led to our work that we're actually going to be presenting after my talk, called Language Models as Zero-Shot Trajectory Generators. And the question we asked is, can a pre-trained GPT-4 output a dense sequence of end effector poses? And you've got some examples here of the task. So what we want to do is get the robot to wipe the plate with the sponge or to shake the mustard bottle, okay? But we want to do this just by getting a language model to predict what those trajectories should be. And we're going to give it access to a language condition segmentation model, which is used to calculate a 3D bounding box. And then we're going to use a single task agnostic prompt. But we're not going to use some of these other properties that other methods have used. For example, trained control policies, predefined control primitives, external trajectory optimizers, or in-context examples. We're not allowing any of this. And this is in contrast to some of the other works in this space, which have allowed all of these other external components to be incorporated. We're trying to just really see what can GPT do on its own without these extra components. Does GPT have an understanding?
Hey, folks in the back, can you please quiet down? There's a few minutes left, so if you could wait 5 minutes or take it outside, then we appreciate it. Thanks.
Thanks. So our investigation, we're really seeing, does GPT natively have an understanding of robotics in order to predict these dense end effector trajectories? And we tested this on a wide range of tasks here. So we've got lots and lots of tasks here, and we're seeing really whether the robot can predict dense sequences of end effector trajectories to solve these tasks without any of these extra properties that some of these other methods have allowed for. And we did this over 26 different tasks. And we took these tasks from other literature. So we didn't just design our own tasks that we knew were going to work. We wanted to do a fair and honest, create a fair and honest understanding of what GPT is capable of. So we took a load of tasks from other papers and we presented the success rates. And we're getting about a 60% success rate on average here. Some methods, some of the tasks work quite well. Some of them don't work so well. But it's really interesting to see that actually GPT, when just given bounding boxes of objects, can predict these dense trajectories in order to solve the tasks. And we also found that if the robot fails to perform a task, it can replan. So here's an example of a failure case where the robot tries to pick up the bowl. What we did is we actually allowed the robot to observe the bounding box moving in the image as the robot performs that task. And then we put in the prompts, in this task agnostic prompt, we gave it the ability to replan given failures. And here the robot is understanding that it needs to have diversity in its solutions. And finally, it succeeds with picking up the bowl because it's realized the first two things it didn't work. Let's have another go. So I'm just going to finalize with my opinion on all of this and really answering that question, do we really need action data or are image and language data enough? So what I'm really talking about is it possible in general to create this pipeline where we take an image and a language command, pass it through an LLM and predict actions? So what we're really saying here is, can a large language model effectively replace a human engineer for each task? Could you get a language model and tell it to solve this task and then design that controller? The problem is, even for classical control, without actually collecting training data, including actions, even experienced roboticists would often need to manually craft a state representation for each task. If they can't do that, then that's where they need the action data and they need to do robot learning. So I think that the problem here really lies in the fact that web scale image datasets are not labeled with detailed descriptions, and therefore these VLMs are not actually that capable of giving us these low-dimensional, these low-level state representations, which would be necessary for the more complex tasks. It might be possible one day, but I don't see that happening in the short term. And so I think all of this is really fun to be exploring the intersection of robotics and language models. And I think language models can certainly help us to do high-level planning and maybe even intermediate-level planning. But I also think it's still important to keep on working on the low-level visual motor control. So I'm still going to carry on working on low-level visual robot learning whilst also exploring the language model ideas. So thanks very much, and I'll take any questions if there are any.
For a great talk. Yeah, time for one question. Thanks, Ed. I've been really interested in this pattern and you've been exploring it a little bit too. Really interesting. So I want to go back to the slide where you showed the tasks that work and I want to get a little more.
You're talking about the last
this
one, yeah.
Yeah, it's really other places, right? And I'm just looking at those bars and I'm trying to think what's going on, like pick up the bowl, didn't do well. Some of them stir the mud with something moan the object together. I'm just wondering, like, what happens in those cases? What do you think is going on? Do you give it a chance to retry on all of them? And what could be done to decrease? I know there's limited fails and they reiterate, and do you think that will help? I'm just curious about what you think, so based on all your experience.
Yeah. So first of all, let's look at the second video on the right, wiping the plate with a sponge. If I bought a robot and it did that, I'd send the robot back because it's not really solving this task. So what we wanted to have is an honest kind of exposure of the capabilities given some kind of relatively simple metrics that we could come up with, okay? So this 60% is an optimistic 60%. In practice, it's not really going to be scrubbing off the muck from that plate. And that kind of goes back to my issue I have of maybe we don't have sufficient state representations. In terms of which tasks work well and which tasks didn't work well, it's sometimes surprising. So you noted pick up the bowl didn't actually work. You might think, oh, it's just a bowl, just pick it up. You know, it's easy. The problem is it's that intersection of the language model and the vision. If the language model just has a bounding box for an object, it doesn't know where the rim of the object is. So it doesn't know where to grasp that object, even though the object is really, really simple. So it's the problem of interfacing the language model with vision, and that's really the main thing here. And most of the times we found that the trajectories were quite sensible. We maybe have a shaking trajectory or a lifting trajectory or a scooping trajectory, but it's actually finding the right place on the object to actually align that trajectory with the object, which is what led to the failure. So that goes back to my point of, well, can we get better visual language models, which will then align much better with the language models themselves, which will then enable some of these tasks that couldn't be solved to actually be solved.
Okay, excellent. We actually have a paper here on exactly that, looking at parts of objects.
Okay.
And being able to use the language to focus in on stuff.
Great. Yeah. No, I think it's, I mean, for you know, you could start feeding into the language model things like affordances and saying, well, this part is graspable, this part isn't. Maybe the language model would do a better job then. What we wanted to do was, we didn't just want to get the best results possible here. We just wanted to say, well, let's imagine we don't have these extra things. What can a language model do just with a bounding box, just out of curiosity to see what we can get from it.
Thanks a lot. Thanks, speaker again. We will now have our two order sessions. So the next talk will be at 4 o'clock with Jonathan. Yeah, so this order session will go until 3:10, and then from 3:10 until 4, there will be the second poster session. Also, quick update for those in the morning. For everybody who has oral, we have our oral presentation in the morning. We have